make my rounds and talk to a lot of people and have a lot of good conversations.
You make your orbits. Now, show me your evidence.
No, typically my friends spin around me.
Nah, dude. I think you're objectively false because you haven't shown me any evidence. And for me to believe anything, I need evidence. I can never take anyone's word for anything in life. I need evidence.
How would you assess evidence?
All right. I know. I have to film myself at a party. Be like, everyone, you're on camera. This is for a Discord argument that I need to win. This is very serious business.
Yeah, dude. Keep it up, guys, and you're going to be needing like 15 licenses just to take a shit in the future.
I know.
You're going to
If you had evidence, for that, I'd be interested in
use the toilet.
I'd be interested if you had evidence for that.
No.
Yeah, you're kind of the evidence in that scenario. Like a fishing license. A fishing license is evidence that you know how to responsibly fish. Or we could like be grown-ass men like we were back in the day. Or
wait, you think fishing licenses are based on...
We could go fishing without licenses because we're just naturally responsible.
Wait, do you think that fishing licenses are like driver's licenses and that they are supposed to be a demonstration of responsibility to fish? Is that your belief? That's what you think they are?
No, it just shows that you're like...
Well, hold on. You said something. Is that what you think?
I mean, I think a fishing license demonstrates that you're quote unquote responsible and you're you understand the legalities of how to fish, what fish to not take, and what fish to take. Shit like that. You know, you just can't go in someone's backyard and land and fish. So
yes, you can.
But yeah, back in the day in America,
you don't need a fishing license to fish on private land.
Not your private land, but let's say I go to my neighbor's private land without permission.
Without permission, then it's a trespassing issue. There's no need for a fishing license to fish on private land.
I mean, I just think there's no need for a fishing license at all. Or
well, mostly you realize why fishing licenses exist?
For money.
Why hunting licenses exist?
For money.
Do you think?
It's so the state can kind of cha-ching cash out.
Yeah, exactly. It's primarily for the collection of fees to support services that enable.
Yeah, but the excuse is you don't know how to fish. Show me your evidence.
Really? Is that what they say? Can you prove? Are you sure about that? What is the process for getting? What state do you live in?
So they can make money.
What state do you live in?
So in order for NASA to continue to make money, they need anybody with a different opinion.
Oh my God. I'm waiting for them to finish so we can start our debate.
What about Colorado?
I'm going to go get a fishing license. Let's figure out what the process is.
You go into your local Walmart.
Yeah,
go to Walmart, show your ID, pay like $50 and walk out.
Yeah, so do you sign a release?
You signed something. I don't know.
You sure about that?
I went into my local Walmart earlier this year to get my fishing license.
Wait,
okay.
Hand the ID, pay $50, sign like 2 things, and go on your way.
Wait, Sea-Line. Wait, Sea-Line, do you want me to come back later?
No, we can. This is a
how we are so confused over fishing license.
I'm a resident. Yada yada yada.
I think Neil deGrasse Tyson is black, and I have evidence.
Bandy, that's you. I remember you.
What's up, Adrian? How's your day going?
I'm pretty sure I just caught you BSing about fishing licenses. So
Bandy, you remember me?
Wait, Mr. Slave, I actually do want to talk to you about something now.
Okay.
He
Yeah,
found,
Mr.
he
Slave,
found a fault in
Slave
my
already-
knowledge about fishing licenses, guys. This guy is
Mr.
really,
Slave already
really
what?
God.
Yeah, I'm listening.
Yeah, I wanted to ask you about Oumuamua and
Oh, what?
why you think it's why you think it's an artificial object and not like some random interstellar object.
What do you think it is? I mean,
I think it's just some random interstellar object.
well, look.
Okay.
So it accelerated in a way that we did not expect, away from the sun. So
I disagree.
what do you mean you disagree?
Oh my God.
Outgassing. What outgassing can explain? What? What's with the peanut gallery?
I'm
Um,
gonna mute
somehow
Bandy.
gas-
I'm gonna mute Bandy because he keeps hot micing during the conversation. Go ahead, I'm listening.
Yeah. Outgassing can produce equivalent velocity changes.
Yeah. But they didn't see any evidence of outgassing, as far as I know. I don't know.
Look at that bad
All
for
right.
talking.
What? What is it?
Oh, he left.
I'm relatively sure that's the current consensus is that outgassing was the cause of the velocity change.
I mean, fine. I mean, if there was outgassing, then fine. As far as I know, there was no outgassing that they noticed at all. I don't, this is not my field. I rely on, input from experts, as they say. And as far as I know, I listened to all the sides, and everyone agrees that we don't have an explanation. So Avi Loeb suggested that if the only explanation that you have is, well, in this case, aliens, however unlikely it is, if it's the only explanation, then it's a scientific explanation. Then for now, it is the scientific explanation. I don't have another explanation. So look, it's not outlandish. So we do assume.
What, aliens isn't outlandish?
No, I mean we have.
Really?
Yeah, I mean we have Fermi's
Come
paradox.
on, man.
Wait, let me finish. So we have Fermi's paradox. Everybody agrees that it is a paradox that life on Earth showed up as soon as Earth allowed life to show up. So life on Earth, it feels like there is always a pressure everywhere in the universe for life to show up, and as soon as conditions are minimally ripe, boom, life shows up. That's what we see from the record, fossil record, whatever.
It's a
Go ahead.
it's a paradox for those that think life is common. For people who know that life isn't common and is statistically improbable, it's a very easy paradox, right?
Wait, did you hear what I just said? Did you understand what I just said about what? Oh, again, I'll repeat. So, like, this
Yeah,
is.
I understand. But it's still hundreds of millions of years after.
I don't know if it's.
I mean,
Look, it was. I don't think it was hundreds of millions, but as far as I understand, as soon as the Earth's crust cooled down just enough to support life, life showed up. Basically, as soon as up to a constant, but like the age of the Earth is the age basically of life on Earth, more or less. It's very close. It's close enough to suggest that life in the universe is a very it's there is a pressure always to create life in the universe. It's not a one-off. It sounds
oh
like.
yeah, I mean, I agree. That
So this creates a paradox, but it doesn't. Everyone agrees that there is a paradox. I didn't create Fermi's paradox, so people talk about this paradox all over the place. All I'm saying is that there should be Okay, somebody's hot micing. So there should be plenty of tech civilizations just everywhere. Okay, so we're unable to see them, and it's a paradox. There's solutions, whatever, but it would make sense that once in a while we would find garbage, alien tech garbage. So
I did post a citation for the fact that they have released that it is outgassing is the most probable cause.
who's they?
NASA. I can get like a paper that's probably
What do you
more.
mean? It's what's their evidence? What's their evidence for outgassing? What?
Based on the composition of it, I think it was nitrogen outgassing would be
Show
the most
me.
likely cause.
Okay,
Consistent.
look. As far as I know, I've heard Avi Loeb say, and I've had an exchange, an email exchange with Avi Loeb because I asked him that because they came. There was a press release that it's resolved. It's resolved. I saw it. Wrote him an email. I said, "What's your response?" And he said, "Yeah, I mean, I'm aware of it, but look into it. You'll see it's nothing. It's the usual nonsense they keep repeating." That's Avi Loeb. And then there is this professor from Cool Worlds from Columbia who is a skeptic. And he said, and he had a show, and he said, let's weigh. I read the book, Avi Loeb's book about aliens. I'm not convinced, except for one piece of evidence, the fact that Oumuamua accelerated in a way that we did not expect. And nothing explained it. And he's a skeptic. So, and I've heard every expert in the field I've heard, whenever they say it's definitely not aliens, they never have evidence. They never say we know what is the cause. They always say we don't know what is the cause. We don't have a single resolution to this paradox, but it's not aliens. So when somebody says that, and I've never heard anyone say that it is. And even Anton Petrov, who said that's the email I sent Avi Loeb. So Anton with his
So, are you thinking that aliens do a flyby, whiz and pass, and they're not dropping in?
no, I don't think so. No, I'm not. I'm not.
Nah,
No, I'm not. I'm not.
It was space alien junk.
Yeah, it was junk.
Oh, okay, I get you. That's actually interesting idea.
Yeah, it's just a piece. Look, it sounds like it's a huge piece of like something like aluminum foil. That's all it is. It's a huge piece of aluminum foil, which makes sense. Like,
Well, why would it speed up? Why would it speed up if nobody's manning it?
speed up.
Solar pressure.
No, speed up towards the. Oh, yes, it behaves like a solar sail.
Yeah,
So-
solar pressure would be the claim, but
I mean,
hydrogen gas outgassing is equally or infinitely more probable, considering aliens versus stuff that's observed all the time is a much stronger.
Okay, yeah, we're repeating ourselves. Let's move to today's topic.
I almost called you Democ, Mr. Slave.
Yes, so me and C-Line, we want to talk about. So C-Line gave a presentation that when I saw it, made me think and forced me to resolve stern-gerlach, which I never resolved before. Like I always, my intuition was that I can resolve it. It shouldn't be much of an issue, but I never really resolved it fully. And I think after I watched Honorable C-Line make his presentation, I wrote a bunch of comments. You can read the comments on the video, and you can see how through the comments I was beginning to rethink everything. And I think I have a completely classical resolution to stern-gerlach.
hey, bro, I could subscribe to you 48 times. I got 48 YouTubes.
I'm going to mute whoever interrupts. So, so before we start, I sent Honorable C-Line, I sent them a video. So I was watching a bunch of YouTube videos of these, this doctor, professor of quantum mechanics, and I asked C-Line, what do you think of this? Do you agree with this? Do you agree with this guy? So in his video, he talks about the video is named, and maybe I'll paste it once again. Copy. How do you copy anything? Copy video URL. Okay, so here is, I'm going to paste in the side chat as I do. Here's a link to the video. This is the Stern-Gerlach experiment. This guy self-identifies as a professor of quantum mechanics or of quantum computing or something. Anyway, so this is his interpretation of the Stern-Gerlach. And he says that the universe is hiding something or another. And this is the standard talking point of modern physics. You know that I usually agree with modern physics, but this is where me and modern physics obviously part ways. I believe the universe is under an obligation to explain itself to me, and modern physics believes that the universe is under no obligation to be understandable. So most, if not all, as far as I know, all modern physicists, all mainstream physicists would say Stern-Gerlach, we don't understand it in any classical way. Now I looked into there was a video that I watched, and this guy was like a quantum mechanics historian, and he brought up historical quotes around the time of the Stern-Gerlach experiment from Stern, from Gerlach, from Bohr, from Einstein, from Born. I don't remember, like, the biggest names, Dirac, Fermi. I don't remember the exact names. No one from the biggest names in history was able, including Einstein, no one was able to explain Stern-Gerlach in any classical way. And as far as I know, until today, no one is able to do that. And people have, to me, what is absolutely nonsensical interpretations. And, I can't share. I wish I could share with you a video, like play it, but if I share it, I don't know, because I'm streaming it, I don't know what would happen. It doesn't matter. You can watch the video. So before we begin, before I give you my interpretation, so C-Line, where do you stand on our inability? Like, can you explain? Do you, like, as they say, before I give my answer, do you want to try and give your answer, a classical physics explanation?
I gotta pull
Yes.
my notes. Just give me 1 sec.
Welcome to Quantum Mechanics for the Working
I
Professional.
have to reset
This
my
is a course meant
school email password to get to my notes.
No problem. If anybody wants, I'll play this video in my stream. I'll give you the current stream where I'm streaming. Here is my stream. You can watch me streaming this guy explaining.
folks with a mild technical background.
Discord has a feature called Activities where you can stream a YouTube video
But I'm
in the Discording.
But I'm streaming. It usually doesn't show up in my stream. Okay, you know what? Let me try it. It usually doesn't show up in my stream, and okay, I'll try. I'll see what. I'll try to do my best. So the Stern-Gerlach experiment, and I'll play. Tell me, can you see when I play it? Do you see that? No, it doesn't, right? Does it play? Can somebody tell me?
What's going on, Globe Gangsters?
Yeah, we see the video.
You can see the video?
Level.
You guys
Can you see
still bending trees or what?
Can you see the video? Can you see me streaming?
Yes.
Okay.
Yes, we can see and hear the video.
Wait, you can or cannot?
Can.
Okay.
C-A-N.
Okay, I'll play it 2 times speed. because he. And I'll skip a little bit because it's not important. So here he is explaining the experiment.
Box up like an oven so that the individual atoms sublimate off of the lump, forming a gas. You can then poke a pinhole in the
Can you still see it? Because I don't know. Okay.
side of that box, causing the silver atoms to spray out like a nozzle. You can then put a screen with another pinhole next to that hole, creating a collimated beam of individual silver atoms. Coming out of the oven, the individual beam of silver atoms have spins pointing in any which direction. Essentially, inside of the box, they were randomly distributed anyway. But generically speaking, the beam of atoms is coming out in a uniform collimated direction, but their spins are pointing in any random direction relative to that beam. In other words, they are a totally unoriented group of atoms, which means that they have a totally unoriented set of magnetic moments. Stern and Gerlach created such a beam of silver atoms and directed it at a large magnet that they designed, specifically to deflect these silver atoms based on their magnetic moment. The beam of atoms went directly through the magnetic field and were deflected, eventually landing on a screen where they left a mark, essentially measuring their position, which measures their deflection from the beam, which measures how much they were affected by the magnetic field. This, in turn, effectively measured the orientation of their spin as the atoms entered the magnetic field. If a silver atom approached the magnet with a spin pointed up, it would be kicked further upward, sending it off at an angle above the beam. If the silver atom approached the magnet with a spin pointed down, it would get kicked further downward, sending it off at an angle below the beam line. You might expect a third scenario where the silver atom's magnetic field, P, was pointed sideways, orthogonal to either of the previous choices, perhaps parallel to the beam line. Classical electrodynamics predicts that such an atom would be undeflected and continue on to hit the screen as if the big magnet weren't even present. The force, in other words, imparted by the magnet, was proportional to the angle between the spin of the individual particle and the beam line. By extension, then, all possible intermediate cases would fill in all other possibilities. The distribution of silver atoms was essentially uniform, after all, so that the beam would have fanned out. In other words, from this perspective, the silver atoms would form a vertical line on the screen. But a vertical line was not what Stern and Gerlach observed. Instead, what they found was that the beam of silver atoms split in two. The observational screen, in other words, had only two distinct clusters of silver atoms, one above and one below the beam line. And that is precisely where the analogy between the silver atom and the baseball spinning breaks down. Welcome to quantum mechanics. This observation's a little weird, so it's worth going over it again. The Stern-Gerlach experiment attempted to measure the orientation of the silver atom's spin. Because they came out of an oven, we expected them to be spinning in all kinds of different directions, and therefore there should be all different types of deflections through the magnetic field, from a little bit up to a lot up, and a little bit down to a lot down. But that's not what was observed. There's only two types of deflections observed: up and down. One way to think about this is in terms of information, data. Silver atoms, like other quantum particles, protons and electrons, can only hold so much information about how they're spinning. In fact, they can only hold one bit of information. That is to say, they can tell you up or down. So if you ever ask a silver atom, hey, which way are you spinning? The only answer it can possibly give based on the storage that it has is either up or down. H bar over 2 minus H bar over 2. And hopefully from this perspective, the difference between a quantum particle and something classical like a baseball becomes clear. A baseball is made up of an immense number of atoms. Each one of those atoms can store more and more information about how the baseball is spinning. So of course we can think about it as spinning 20 rotations per second, 50 rotations per second, 2 rotations per second in various directions. It has more capacity, more storage for that information. A lot of the weirdness associated with quantum mechanics, a lot of the peculiarities that we will meet are associated to the fact that the universe simply doesn't have the information to answer the questions that you're looking to ask. Because two-level systems like the spin of a silver atom or an electron or a proton only can tell you things like up or down, yes or no, true or false, they behave kind of like a bit from information theory, right? A Boolean variable. But because they obey the laws of quantum mechanics, which we will get to shortly, we call them quantum bits or qubits for short.
And then he goes into mathematics, but the point is, okay, I mean, so at this point I need to ask C-line, do you agree or disagree with this guy, or can you offer an explanation to stern-gerlach?
Yeah, do you guys? I want to record as well, so I can put it on.
What?
Stupid.
No, do not let him record. He's gonna put it on Flurf argument of shame.
He's not a flirt, so he doesn't end up there. Did you
Yeah.
figure out why neutrons are a problem yet? Level.
Here we go. Did you figure out why we can't bend 90 degrees yet? Right?
Anyway, C-line, wait, are you trying to do
I've been
something?
90 degrees all the time. I told you that already. That's kind of my thing on the weekends. Sorry, go ahead, Mr. Slade.
C-line, where? So okay, C-line, where are we? So do you want to offer your explanation to? Okay, go ahead.
Pull up my slides. I have some slides, and then.
So he said that classically we expected a spread from all the way up to all the way down and everything in between. And and this is where quantum mechanics kicks in. That in quantum mechanics, there's a bit, there's not enough information. The information. All right, I say complete and utter nonsense. Classically, we should have. And anyway, I'm not gonna give away my answer, even though I've already debated this and it's already been recorded. But I want you. I'm curious, before I give my answer and show you my answer, I'm curious what your answer is.
All right, cool. So do you see my screen?
Let me watch it. Yes.
Wait,
Okay.
before we continue, Mr. Slave, what are you?
No. I'm gonna mute you because I want to concentrate. Go ahead, C-Line.
He's a troll.
Yeah. All right, cool. So just for the sake of the audience, we'll try to keep this educational.
Yeah, I muted high up level. Yeah.
Classical mechanics describes things as proceeding deterministically according to known laws of physics. Now, of course, in practice, there will be variation, but the expectation would be that the state of a system is continuous and up to uncertainty in the inputs can be determined deterministically. We also will just need to know the basics of, I'll change this since Eric's complained about it. Electromagnetism, the basics there. There's what's called the Lorentz force, which is the combined force of an electric and magnetic field, which also interacts with the velocity of the particle. So if a charged particle moves through a magnetic field, it experiences a Lorentz force. We know that magnetism can be induced by different things. And I'm going to skip ahead here. Magnetic moment. So we should all know that by their nature, atoms are balanced in charge. They have the same number of protons and electrons. So that produces a net neutral charge. However, we can also know some atoms have a magnetic field. This is called the magnetic moment. We can describe the magnetic moment based on the model of an electron moving in a ring or a current ring. Thus, the magnetic moment is a function of the charge and the angular momentum. Hence, magnets themselves, or atoms themselves, can be thought of as magnets, kind of, sort of, when they possess a magnetic moment. And that's basically going to just be induced by the movement of electrons. So due to an imbalance in electrons in the orbitals, we'll determine whether they have the degree of their magnetic moment. So prior to Stern-Gerlach, we had the Bohr model, which suggested that there were some level of quantized states for atoms. This was sort of the first suggestion, but it was back in the day, physicists actually felt exactly as Mr. Slave does, and they believed that it was nonsense. The Stern here is the Stern-Gerlach guy and says that with another physicist, Max von Laue, said, if this nonsense of Bohr should in the end prove to be right, we will quit physics. All this is important because it leads us basically into the discussion of the Stern-Gerlach. So particle beam experiments were set up before this, but the idea behind the Stern-Gerlach experiment is that of a splitting force. We mentioned that the Lorentz force is a function of the charge of a particle. So as a charged particle moves through an electric and or magnetic field, it will experience a force according to the Lorentz force. Such a force will not exist for a particle of zero charge, like a silver atom, and nonetheless will experience a splitting force. We then go to some lecture notes here. Again, so this gets into the sort of fundamentals of why quantum mechanics is accepted. It has nothing to do, in fact, it is in opposition to the fact that it doesn't make sense. Scientists did not want to believe that this theory is true. They were forced to adopt it as true based on the evidence. So this is, again, just going into a description of an atom being a bar magnet based on a magnetic moment. And you can see the sort of like current rings that are formed by the electrons. This is now important because basically you can get torque on the different poles of the magnet. You know, if there's a magnetic moment, it has this north and south polarity. That was shown by the direction of the vector in the slide that I showed before. these are some lecture notes, just providing. I'll post these in the physics channel, but these are lecture notes that show the torques that will be produced by different arrangements. But this basically is the setup here. If we are in an inhomogeneous magnetic field and we send magnets at a constant velocity through this field, they will basically experience a precession, which is precisely the same sort of precession as occurs in gyroscopes. This gives rise to a property of particles and indeed atoms, which is called spin. And all of this is just to say that there is the lead up to the Stern-Gerlach experiment is this idea that orbital angular momentum, or spin, which is the determinant of the magnetic state of the atom. Well, I guess it's a property that relates to the magnetic moment. The orbital angular momentum, or spin, could take potentially a continuous range of values, which was the expectation of classical mechanics, right? We just said that at the beginning. Under a classical theory, the state would have to be continuous, not taking discrete states. And in fact, what Gerlach found or Stern found, this is another great quote by Gerlach as well: "No experiment is so dumb that it should not be tried." Again, pointing to the fact that quantum mechanics was not sort of concocted as an ad hoc explanation. It was a required and very unhappy conclusion of the physics of the early 20th century. But yeah, here again, the orbital angular momentum is like, he believed that the orbital angular momentum would be limited to two states, as in opposition to the classical theory. According to classical theory, a particle beam of silver atoms passing through an inhomogeneous magnetic field will experience that splitting force, because the property of spin, in the same way as gyroscopes have a resistance to the application of torque, which is the cause of the property of precession in gyroscopes. Similarly, atoms with a magnetic moment having non-zero spin will have a precession, which is caused by the application of the splitting force, causing the beam to, in the classical expectation, take a continuous distribution of states on the other side. This leads us into the Stern-Gerlach apparatus. Here we have a silver atom source that passes through two collimators, passing through an inhomogeneous magnetic field, being split then into two states in the non-classical theory and a continuous range of states in the classical theory. What was observed? The classical result was not observed. The left-hand side shows the particle beam prior to passing through the splitting field. That is just due, the variance is due to the collimation of the beam, that it can only be collimated so much, so it produces this spread as a function of the base beam spread. You'll notice that width does not change, but the application of the inhomogeneous magnetic field causes a splitting force, which you can see splits quite nicely where the atoms land into two separate distributions. That's mine. So that's the interpretation of the Stern-Gerlach experiment, is that spin is a quantized property, which is a determinant of magnetic moment. So I'm not sure how you can explain that classically, but that would be the position that I would take. And we can go into more detail from there, but
yeah, okay. So let me ask you, if I take a compass and I put it in the magnetic field, what do you expect the compass to do?
The compass is going to point to the direction of the stronger magnet.
Okay. And if I take tiny magnets, like if I take a magnet and I grind it into a powder and I throw in just one speck of dust of this powder, which is still magnetic, and I throw it into the Stern-Gerlach magnetic field, what do you expect it to do, this speck of magnetic dust, which is a tiny compass, like a speck of dust sized compass?
So it will still have a orientation towards the stronger magnet, which in this case is the top magnet. But because the spin itself affects the magnetic moment, all atoms that pass through the detector do not start with the same magnetic moment, exactly the same orientation of their magnetic moment.
No.
So
No.
as they move through the field, they experience precession.
No. I'm saying, okay, we'll come back to the silver atoms. I'm saying if I take a magnet and I grind it into a powder, and I take one speck of dust of this powder, which still is a tiny. Right now, I'm holding a tiny compass, and I'm gonna throw that into the stern-gerlach magnetic field. What do you expect that speck of magnetized dust to do?
It would depend on its initial orientation. So
Right.
if we have,
Right.
and this is just shown in the lecture notes here, but a priori, right? And then we could talk about the consequences of that later. But
wait, what do you mean later? What? I'm asking.
Like, So, but basically, like, so here's an example, right? So this is a inhomogeneous magnetic field stronger on the South Pole. But this is 3 to 4 different examples of orientations of magnets passing through the field. Every magnet possesses a dipole. There's no unipolar magnet. Therefore, the expected behavior of the magnet in the field depends on its relative orientation.
Sure. So I'm throwing random specks of magnetized dust, tiny compasses. I'm throwing into the Stern-Gerlach experiment. Like, what do you expect that stream of tiny compasses to do? Like, we're not going to silver atoms right now. So I'm just talking about tiny magnets. Would you?
It's going to do it classically. It's going to do this. There's going to be a spread.
Why?
Because the splitting force is going to affect the precession of the magnet as it moves through the field according to its magnetic moment. And that precession is going to interact with its initial velocity and position in the field to determine its final position.
Wait. Let's assume it's not spinning. A non-spinning magnet.
Yeah, but spin in this context is abstract. When we talk about spin, it's not actually spinning. But every single magnetic particle that we send through there is going to have a variation in this property we call spin, or its magnetic moment.
Okay,
that is going to cause a split. The effect is what's called the splitting force.
Wait, one second. No. Let me ask my question. Let me be more clear. So I'm holding a speck of dust that is magnetized. It's basically a tiny compass. You agree that if I hold a compass in the magnetic field, it will align with the magnetic field, right?
Correct, but every magnet, we'll have to think about that. So if it's an inhomogeneous magnetic field, eventually, yes, it should align with the magnetic field, but depending on how you oriented the compass at the start, there's going to be a starting orientation and an ending orientation.
Yeah.
And if you just left it statically in the magnetic field, then yes, it will align in the direction of the stronger magnet. But the whole point of this experiment is that we're moving things through the field. There's no static thing. So if you're asking what would happen if a single particle was placed and held trapped in this magnetic field, yes, it's eventually going to align with the magnetic field, regardless of its initial state.
Wait, so...
Well, not necessarily, actually, because in certain circumstances, there's basically a zero force. I don't know, for an inhomogeneous field, though, because if it's a homogeneous field, like here's an example where all 3 of these are in equilibrium, but there's stable and unstable equilibrium. When it's inhomogeneous, though, I believe, I think that if it's in an inhomogeneous field, it will eventually align.
But will it always align the same way, or will it depend on the initial condition? Like sometimes will it align north and sometimes south, like 50-50 randomly, or because
Well, like in this case, this magnet is going to be stable. I think there's potentially more than one stable equilibrium even in an homogeneous field. So I think it still would depend on the initial state. I don't think you can get around that. I think there's multiple equilibria that will be reached as a function of the input state.
it wouldn't just align with the magnetic lines? Like,
well, what I'm telling you is that yes, but if you think about it, I'm not sure. I have to think about that more. But I think that there's going to be multiple states of equilibrium that can be reached. That's my intuition, but I'd have to verify that.
But look, this is the question. So I don't know. Like, my intuition was that classically, if you take a compass and you move it through or place it in the stern-gerlach field, it will either point up or down depending on the initial condition. If it's closer to the up, it will align up. If it's closer to the down, it will align down. That's
perhaps, but the tricky thing is that the field is stronger in one direction, creating a gradient.
Yeah, but
I think we're saying the same thing. I think that there will be an equilibrium that's reached that's dependent on initial state.
Right,
I
but
think that's true.
No.
Is there any other physics nerds that want to correct that?
Okay, so I think we need to reconvene because I need to look into this. But I'll tell you what I'm thinking. My thoughts were that the classic, if you took a tiny magnet, like I took a magnet and you ground it to a powder and you threw in the little pieces of this powder through the stern-gerlach. So I would have thought that each randomly aligned tiny compass that I'm throwing in, each one will align, well, randomly either up or down. 50% will align up, 50% will align down. And as I'm throwing them in, I'll get the splitting data and I'll reproduce stern-gerlach. That was my intuition. So I would have expected them to first start with that experiment. I would have loved to see that experiment. Show me that classically, you claim classically, okay, could you show me classically what would happen? So that's
Dr. Weasel. We need Dr. Weasel's help to resolve this, perhaps.
okay. Look, so that's my intuition. I mean, if this is true, if classically I can reproduce stern-gerlach, then I can claim, okay, let's now show that a silver atom really is just a tiny microscopic compass, and then that's my intuition. But I don't know. That's the question. So I need to, right? I need someone. I don't know magnetism. I don't know classical physics.
Me neither. I've
Yeah.
only taken physics 1 and 2.
Yeah. So
Well, you have the equations for it there in your presentation, C-line.
the equation,
And you can,
the equation is
the equation for the classical equation simply tells you that the
force
torque is going to be proportional to the initial state, the initial vector.
So the
And
force,
since the vector can be continuously distributed, therefore, by classical physics, it should be producing a continuous line on the other end.
wait,
Yeah.
the force.
Can I ask a question,
No,
Sealand? Sorry,
no.
I've been on server mute. I've been on server mute for 20 minutes.
Wait, but
in order to resist, and now I have to ask a question. But yes, but I have to ask him a question.
Yeah, go ahead.
Sealand, why are we doing this? I know why you're doing this. You're practicing, right? But if this man, this intellectual troll, have you discussed with him?
Okay, I muted this guy, so I'll leave and we can continue some other time. All right, so we're done with that. That was actually very interesting, so I need to look into that further. So that's a good question. That's a good question. Very interesting. That was very interesting. Interesting enough that I'm done with that. All right. So the next order of business would actually be to look into. Oh my God, I keep closing my YouTube channel. Let's try this. Did it close? No, it's just good enough. All right. Okay. So I don't know how long did we do. There's probably half an hour. It's not enough. Okay. Let's see the electric field. I would just look into actual magnetism. I need to understand actual magnetism. So we can do Dr. Physics playlists. He has magnetism.
Hello. Today we continue with our A-level physics revision series looking at the subject of electricity. And what is electricity? Well, it's a current flowing in a wire. But what actually does flow in a wire? If this is the wire, we actually have a flow of electrons. It's the electrons in the wire that constitute the current, and they will be attracted to the positive terminal, flowing away from the negative terminal. Now, for historical reasons, we always draw the current as flowing in the opposite direction from plus to minus, but in fact the current is simply a flow of electrons which travels in the opposite direction to what's called the conventional current. That's for historical reasons. Each electron carries a charge of 1.6 times 10 to the minus 19.
But maybe we can skip to magnetism. Maxwell Fresnel equation, polarization, electro waveguide absorption. So that guy obviously reacted because this was too close for comfort. Like, how can they entertain that I am able to question Einstein and all the rest of the names? I'm actually questioning the whole thing. The whole thing could come down collapsing. I just don't want to waste my time. My time is valuable, and I'd rather do something productive. That was very good, because now I actually need to look into it. So here, maybe electromagnetism.
So today we're going to continue in our A-level physics revision series by looking at the subject of electromagnetism. We've already considered electricity, so now let's think about magnetism. What is a magnet? A magnet has a north pole and a south pole, and the magnetic field flows from the north pole to the south pole. Now, the important thing about a magnet and what distinguishes it from an electric charge is that whilst you can have an electric charge that is positive or negative, for example, a proton is positively charged, an electron is negatively charged, and you can have those entirely separately, you can never have a north pole on its own or a south pole on its own. Theoretically, they could exist, but they've never been found. In other words, you can never have a single pole. They always come together, and the magnetic field flows from north to south. The Earth is, in fact, a magnet. It's tipped to one side, but it's not.
How would you have one? Okay, I don't know.
North pole and its south pole are here, and the magnetic field lines flow from north to south. And that's the reason that particles get trapped by the Earth's magnetic field. Magnetic field is sometimes called flux density, and its units are Tesla. You'll remember that in relation to charges, we say that like charges repel, unlike charges attract. And it's the same with magnetism. Like poles repel. Bring two north poles of a magnet together, and they will repel. And the reason is that their fields interact. They push against one another. Whereas if you bring a north pole and a south pole together, then the field lines readily go from north to south and create an attractive force. So like poles repel, unlike poles attract. Now, a current flowing in a wire, here's a current I, flowing in a wire, will create a magnetic field around that wire. And which way does that magnetic field go? Well, we have to...
And Celine mentioned that the silver atom will process. Why would it process? It's just because of the angular momentum? So would a spinning magnet? We need to reproduce this with tiny spinning magnets. I mean, show me with tiny spinning magnets. Show me, how difficult could it be? Show me how a tiny spinning magnet does not align. I guess it would never lose its energy. This is what Einstein said. Why would it ever lose its energy? It's going to forever precess. Because it has an angular momentum. Whatever you're trying to do, it's going to conserve it's not going to lose its angular momentum. Why would it lose its angular momentum? Unless they interact with each other. Right, it's in a vacuum. Are you sending them one at a time? I don't think they're sending them one at a time. So they might be interacting with each other and you might be getting friction. Maybe that's causing it. They're bumping into each other and losing energy and losing angular momentum, and the angular momentum gets aligned. But that's what Einstein said. It should take 100 years. So it's not, the problem is of the precession. That's the problem. Everything else makes sense. It's because of the spin and the angular momentum. So whatever it is, it's gonna become a pendulum. It's gonna undulate. It's gonna precess. And there's no reason for it to stop precessing. It's not like in real life that there is friction. There's no friction. Well, maybe there is friction. Why would there be friction? Let me see messages. I don't see any messages. Okay. Wait, let me go to my... So I don't think there's anything else that I can do at this point except for... That's the problem. The problem is, I mean, we need to reproduce this. The question is, how do we shed the energy? How does a tiny magnet align? That's the problem. How does a tiny magnet end up aligning? So a non-spinning magnet, you can say it will align. Yes, sir. Sure, I'm coming. Yes. Wait, why am I... Okay. Yes.
Come back, bro. The stage is yours.
No, I'm thinking this is what Einstein said, that it will require 100 years for the silver atoms to align with the field. It's just that they're not shedding energy. They're not shedding their angular momentum. If we didn't if they didn't have angular momentum, I guess it would be explained easily. The problem is that silver atoms cannot shed angular momentum, so that's the problem. Now, I know that they threw them in together. The silver atoms were not one at a time. So I think the numbers were actually very big. We're talking something like 10 to the fourth atoms going in per second. I mean, these are very big numbers. So it could be that these atoms were interacting and bouncing against each other and, causing friction and destroying each other's angular momentum. And through that, they became aligned. Look, I just don't know enough. So I don't have a problem to concede. I honestly just don't know enough. Before I say that this universe conspires and stuff like that, which is, I would never say that. I mean, I would like to reproduce this experiment with a single silver atom at a time, with tiny magnets, tiny rotating magnets. There's plenty of ways to reproduce this experiment, and feel more what's going on before we give up and create quantum computing and dogs and cats alive and dead at the same time all over the universe. That's what I'm saying. There's enough foundation to think about this problem mechanically. There's enough foundation to simulate this with tiny magnets, with powdered magnets, and
Sounds like a paper you need to write then, or an experiment that you need to perform.
No, anyone listening to the stream, it's
No, you don't have to support your contentions.
no. I'm a free.
That's an interesting way to do science.
Yeah, according to my science, before I do science, first of all, I'm a free person. I'm a happy man, and I do whatever I want. And if I feel like doing this experiment, I will. And if I don't, I will not. And I said, I'm throwing enough. I'm saying enough. There's enough. I'm saying that I can play with. There's enough room for further experiments before we say the universe, qubits, quantum computing. Give me $1 trillion. Let's throw another $1 trillion down the drain. That's all I'm saying.
Well, 100 years worth of physicists have thought about this and agree with it. You disagree, so you have the burden of proof. Otherwise, your claims are going to be dismissed without evidence, which is exactly the amount of evidence you have provided so far. Either formulate a theory, write it into a paper, and propose some experiments, or even better, do the experiments yourself, or otherwise your contentions are simply dismissed as lacking basis.
Sea Lion, are you here?
Let's all go to the lobby. Let's all go to the lobby.
Anyway,
Sea Lion.
Wait, who is the person who just spoke? Very Totoro as usual. Totoro, please don't be nice. I'm not hurting anyone's feelings. This is a nice conversation.
I'm simply telling you how science works.
Mr. Slave.
One second. So, Mr. Totoro, you're not telling me anything, and I'm not telling you anything. We're having a conversation. I told you my definition of science. On any given day, I define science for me. You're welcome to follow my science. You can not or do follow my science. You can propose your science, and I can choose to follow or not to follow your science. We're free people. We're free men. So by my science, I'm not obligated to do anything. And I feel at this point that this is, to say the least, inconclusive. To say that, and now to your point, that 100 years of physicists, including big names that I admire and I have the biggest respect for, of course, including Einstein and everyone else. But
okay, wrap it up. Let other people speak. Okay.
Yes, thank you. I'm done. Go ahead.
I have to go, and then I'm going to come right back. I've been listening to the whole conversation on my drive home. I have to run an errand really quick. When I get back, though, Mr. Slave, I want to talk more about your experiment idea of like grinding up a magnet and sending it through a stern-gerlach, because I can tell you how that will happen.
Okay.
Like what will happen with that.
Okay.
But first, I need to run a thing.
Okay. Oh, it was Tapioca Weasel, and I didn't let him speak. Jesus. I have a lot of respect, of course, for Tapioca.
Oh, you feel bad now, don't you? Now that you know he's a PhD and wasn't just some Discord rando.
Look, besides being a PhD, he treated me with more respect, like a lot of respect. So just because, even just for that, plus he's very knowledgeable, and he's a great guy. You're a great guy too. So there's plenty of great people in this room. So, but some of them are very not great people. Anyway, look,
But who treats you with the most respect, Mr. Slave? You got to give it up to me, right?
Definitely,
Yeah.
you're
Yeah,
up there,
yeah.
definitely. Anyway, look, okay, I mean, he's going to propose what will happen when we grind up. I'm not saying, okay, I'm curious what will happen, but the way I see it, if right, as far as I know, because I've watched a lot of videos and I've watched the original videos from like 1,000 years ago, like black and white, from the NSF and stuff like that they reproduced this experiment, and I watched very carefully every step what they said, and the number of atoms going through per second is significant. And we might even be able to see, we might be able to see these atoms like a, as smoke or something. It could even be that the light in the room might be destroying their angular momentum. I don't know. I just don't know. Right, because they need to shed the energy of the angular momentum. This is what Einstein said, and sure. Look, uh, look. Most of quantum mechanics is classical to me by far. Certain experiments in quantum mechanics we cannot explain. Okay, it's like you go to see a magic show, you see a magician conducting some magic, and you cannot explain it. So before you say he's doing actual magic and he's a real magician, before I say that, I say, for now, I don't know. Maybe one day I'll figure it out. Maybe I'll never figure it out. There's some magicians who they say they turn to the dark side, and they become like Uri Gellers, and they actually claim to have ESP and actual powers, and they turn it into a lot of money. So, before we believe nonsense, we should, say, okay, for now, we don't understand it. For now, we don't understand the double slit. It's just a bunch of experiments we don't understand. We don't have to lose our minds, because we're basically losing our minds when we say that cats are dead.
Didn't you start your whole ether thing? Didn't you start your whole ether thing because you didn't understand something or couldn't understand something?
I wouldn't say that. Wait, did you just imitate my
No, he wouldn't do that.
Well, he would get muted.
I didn't do that. Someone
Okay.
else did.
Okay, whoever did that, that's very mean. Please.
But isn't that what you did? You thought you couldn't understand the cat being alive and not being alive at the same time as the concept, so you started your quantum ether.
Look, it's definitional. So if I try to understand something, it doesn't make any sense to me, and this is a repeating issue with modern physics. Yeah. Then I'm not saying the ether directly came out of it. I mean, the ether came indirectly out of it. So initially, I decided one night, no more. From now on, I'm redefining my science to be mechanical. Simple, mechanical, understandable. No more of this nonsense that the universe is under no obligation to be understood by me. Enough of that. I gave that a chance. That got me nowhere. I still don't understand anything in modern physics. So I don't like that. So I decided to redefine.
What do you think the point of what I said before is?
What do you mean?
So I spoke up and I asked you, didn't you do your whole ether thing because you couldn't understand Schrodinger's equation or Schrodinger's cat, the concept of it?
But
so what do you think the point of me bringing that up was?
No. So I knew, look, I don't remember my own evolution, but as far as I know, as far as I remember, I always knew that Schrodinger invented Schrodinger's cat. Somebody's hot micing. You're hot micing. Dog, you're hot micing.
Yeah, I'll hot mic that happen.
Okay.
I try
So-
not to, but it happens.
It's okay. So as far as I remember, I always knew this complete misunderstanding of history that Schrodinger invented Schrodinger's cat thought experiment to mock the people who basically the side of Bohr. So Bohr ended up being this woo.
Okay, I'm going to ask you the same question again. What do you think the point of me bringing that up to you was?
I'm gonna mute you. Have a great rest of your life. And if no one has anything, so like I don't know what to do. Like I don't like being cut off and being mistreated. So mm, I don't know what to do. I mean,
I want to engage you.
no, he's very mean and he's cutting me off. Oh, I'm being okay. That's good. All right, they want to be mean and demean me and hurt my feelings. I don't want to waste my time. That's the problem. That is a problem, and so that's the end of that. That's the end of that. What else do we do at this point? I don't know if this is helpful. I don't know. Well, I can give it a shot, maybe a little bit.
Apply what's called the
Because the problem is that I don't have access to perform this experiment again, one atom at a time in the dark, and just keep on. Let me think. Right, the first time they ran the experiment, there was a spread. So when the magnetic field is not strong, they get a spread. Now, when the magnetic field is not strong, they were getting a spread. They strengthened the magnetic field, and they were getting a spread. And the claim is there shouldn't be this spread because Einstein explained that the atoms shouldn't shed their angular momentum. But what's his evidence? He did the calculations. He said it would take 100 years for them to shed I don't know. I don't know what he knew about this experiment. I don't know. There's too many unknowns.
corkscrew rule. Think about a corkscrew. If you twist it clockwise, you drive the corkscrew into the bottle. If you twist it anti-clockwise, you pull the corkscrew out of the bottle. It's the same as a screwdriver. If you turn the screwdriver clockwise, you drive the screw in. If you turn the screwdriver anti-clockwise, you pull the screw out. And that's the principle we apply here. If the current is, for example, going into the paper, then just as the screw or the corkscrew goes in, that means if you want it to go in, you have to turn it clockwise. And so the magnetic field will go clockwise. If, on the other hand, the current is coming out of the paper, then this is coming out, then the field will be anti-clockwise. Now, if you put a wire carrying a current in a
But when it goes in, we write an X.
magnetic field, here is a magnetic field north to south, and here is a wire which you have to imagine is actually coming out of the paper, and the current is flowing towards me. What you will find is that there will be a force on that wire, and it will move. And the reason is that there is a field between north and south, but there's also a magnetic field caused by the current going through the wire. And that magnetic field caused by the current in the wire interacts with the magnetic field that you've got on either side, and that will cause the wire to move. But in what direction? And here we have to apply Fleming's left-hand rule. If you take your left hand and get your thumb, first finger, and second finger in this shape, that enables you to tell what is going to happen to the wire. The rule is very simple. Your thumb is the motion of the wire, motion. Your first finger, is the field, the magnetic field. Your second finger, second, is the current. So thumb motion for first field, first finger, field, and second finger, current. And now if you like
Thumb motion. This is second. This is thumb. I don't know. Anyway, what I already forgot. Why doesn't he write it down? This is good stuff.
and get your thumb, first finger, and second finger in this shape. That enables you to tell what is going to happen to the wire. The rule is very simple. Your thumb is the motion of the wire, motion. Your first finger,
Thumb is motion. What was
what is going to happen to the wire. The rule is very simple. Your thumb is the motion of the wire, motion. Your first finger, is the field, the magnetic field. Your thumb is the motion of the wire, motion. Your first finger, is the field, the magnetic
First finger is field. Okay.
field. Your second finger, second, is the current. So thumb.
Current, field, current. Motion, field, current. Motion is the thumb. First is the field. Second is the current.
Motion, the first field, first finger, field, and second finger, current. And now if you line those up, you will find out in which direction the motion will be. So in this case, the field is north to south. The current is coming.
Okay. So the thumb is the motion. The first is the field. The second is the current. So the current is this way. Oh, how do you do that? The current is in an angle. How do you do that? Okay, you just have to assume it's down. If the current is down and the field, then the motion is towards us. It's going to move towards us. I think, no?
That's this finger, is coming out of the paper, and that means the motion, which is the thumb, is upwards. This tells us that.
Oh. Oh, yeah. Wait, what? I didn't understand the question.
Line those up, you will find out in which direction the motion will be. Second, put a wire carrying a current in a magnetic field. Here is a magnetic field, north to south, and here is a wire which you have to.
So the field, the first finger, is north to south.
Imagine it's actually coming out of the paper, and the current is flowing towards me.
What's coming out of the paper?
Now, if you put a wire carrying a current in a magnetic field, here is a magnetic field, north to south, and here is a wire which you have to imagine is actually coming out of the paper, and the current is.
Oh, it's coming out of the paper. Okay. Then the motion is up. Okay.
It's flowing towards me. What you will find is that there will be a force on that wire, and it will move. And the reason is that there is a field between north and south, but there's also a magnetic field caused by the current going through the wire. And that magnetic field caused by the current in the wire interacts with the magnetic field that you've got on either side, and that will cause the wire to move. But in what direction?
So we would use, if that's the current, then we use the right-hand rule, then it rotates counterclockwise.
And here we have to apply Fleming's left-hand rule. If you take your left hand and get your thumb, first finger, and second finger in this shape, that enables you to tell what is going to happen to the wire. The rule is very simple. Your thumb is the motion of the wire, motion. Your first finger, so thumb, and now if you line those up, you will find out in which direction the motion will be. So in this case, the field is north to south. The current is coming, that's this finger, is coming out of the paper, and that means the motion, which is the thumb, is upwards. This tells us that the wire will be pushed up. The wire will be pushed in an upwards direction. In other words, there's a force acting on the wire. What is the value of that force? Well, the force is equal to the strength of the magnetic field, which we use the letter B to represent, multiplied by the current flowing in the wire, which is I, multiplied by the length of the wire, which is L. And it's important to notice that that L is not the entire length of the wire, but the length of the wire that is in the magnetic field. And you'll notice that in this example, the magnetic field B and the current I are at right angles because the field is essentially going left to right, and the current is coming out of the paper. So it's actually coming straight up at me, and that's at right angles. What happens if B and I are not at right angles? Let's suppose, for example, that B is in this direction and I is in this direction. What then is the value of the force? Well, the angle between the two is theta, and the force will then be BIL, the same as it was before, but now multiplied by the sine of the angle between them. And you can see that when theta is 90 degrees, the sine of 90 is 1. But when theta is 0, the force is 0. In other words, if...
It's so bizarre. I'm offering them a solution for an entire edifice of nonsense. And what they say is, you have to conduct the experiment. Like, we don't care. Like, we don't care. You have to conduct and you have to prove to us. Until then, what? You're going to waste your time? So until then, you will waste your time, so you're not curious?
Will then be BIL, the same as it was before, but now multiplied by the sine of the angle between them. And you can see that when theta is 90 degrees, the sine of 90 is 1. But when theta is 0, the force is 0. In other words, if the magnetic field and the current are both in the same direction, there will be no force. If we look at our left-hand rule again, the magnetic 90 degree L is not out of the paper B, and the current.
So it's BIL, and it's the strength of the magnetic field. The I, the current, the L, the length.
I are at right angles because the field.
But that's the right angles.
Is essentially going left to right, and the current is coming out of the paper, so it's actually coming straight up at me, and that's at right angles. What happens if B and I are not at right angles? Let's suppose, for example, that B is in this direction and I is in this direction.
Okay, so let's say that the current is not at right angles, because right now the current is perfectly at right angles, so it's the maximum force, I guess. But what if it's not at right angles? So we want the 90 degrees to be, so we want the sine. Okay, it's the sine theta between them. So that if they're at sine theta equals 0, sine theta is 0. So we want the force to be 0 if they're aligned. So it's basically the cross product. No, it's just a sine.
What then is the value of the force? Well, the angle between the two is theta, and the force will then be BIL.
I just wish people would have normal conversations. Like, why are people trying to hurt your feelings? Like, what's the purpose of that? Like, what? Show me the gain. Okay, you hurt my feelings. Great. You're all together. You're all one tribe, and I'm not part of your tribe, so you're gonna make fun of me. Okay, all right. Nice going. Basically, a bunch of apes. Hmm. Mm-hmm.
The same as it was before, but now multiplied by the sine of the angle between them. And you can see that when theta is 90 degrees, the sine of 90 is 1. But when theta is 0, the force is 0. In other words, if the magnetic field and the current are both in the same direction, there will be no force. If we look at our left-hand rule again, this is with all of the fingers at right angles to one another. But if we take the field and the current, we can actually narrow the angle. But you'll notice that my thumb is still...
Oh, this is the left-hand rule? So, the field and the current are at right angles. The smaller the difference, then the smaller the motion, the smaller the force.
Perpendicular. So where you have the field and the current in a particular plane, the force will always be perpendicular to that plane.
Mm-hmm.
What is the value of a field?
So it is a cross product.
Field close to a wire carrying a current. In other words, here's the magnetic field around the wire carrying the current.
This is the current, which is the opposite direction of the electron's motion.
By experiment, it has been found that the magnetic field is equal to mu naught I divided by 2 pi r, where mu naught is what is called the permeability of free space. I is the value of the current in the wire. 2 pi is just what we know pi to be. And r is the distance of the magnetic field from the wire. A solenoid is a coil of wire through which the current passes. And the magnetic field inside the solenoid is again given by experimental observation to be mu naught times n times I, where mu naught is once again the permeability of free space, n is the number of turns in the wire, and I is the current. There are ways.
Very interesting. If this is experimental, I doubt it. We can probably derive it. What's amazing is the magnetic field where? Inside? Well, that's like a closed wire. What's the magnetic field inside a closed wire? And it's probably mu I. We can probably prove that a closed wire gives us a magnetic field inside the wire homogeneous mu I. turn every coil we coil gives us another mu I, and they add up. Interesting.
Again, the permeability of free space. N is the number of turns in the wire, and I is the current. There are ways of measuring the magnitude of the force. We could, for example, use a simple balance. Here is a balance. On the one side, we can put weights so that we can measure the weight. On the other side, we perhaps put a coil of wire around which a current is flowing, and we put that between a magnetic field, north to south. And there will be a force on that cable. In which direction will that force operate? Well, the current is going into the paper, the field is going in this direction, so the thumb motion is down. You see, the current is going into the paper, the field is in this direction, and therefore the motion is down.
On the balance level, magnetic force. Is it a coiled wire?
On the one side, we can put weights so that we can measure the weight. On the other side, we perhaps put a coil of wire around which a current is flowing, and we put that between a magnetic field. North to south. And there will be a force on that cable. In which direction will that force operate?
Well, which wire? Well, there's two wires. So which wire is in the magnetic field? If it's the bottom, then it's going away from us. The current is down. The field is north to south. The current, if the current is away, if I understand it correctly, the current is away, then the force is down. That's why it's balancing the weight.
Well, the current is going into the paper, the field is going in this direction, so the thumb motion is down. You see, the current is going into the paper, the field is in this direction, and therefore the motion is down.
So I keep muting people who hurt my feelings, so they mute me. They server mute me because people keep attacking me personally. Very strange. You can make a motor by placing a coil of wire carrying a current in the magnetic field. Right, so these two this is force down and this is up. So this will start turning counterclockwise.
Let's apply the left-hand rule to this side, this part of the current. Well, the field is in this direction, north to south. The current is going downwards, and so the motion will be, my thumb, will be up. So here, the force will be up. But I think you can see that on the other side, where the current is going in the other direction, the force will be down. And that will cause this coil to flip. It will rotate. Of course, it won't rotate very far, but if we arrange it so that we've got what are called commutators, that is to say, fixed gadgets, so that as this flips around, this wire will attach to that commutator, and this wire will attach to that commutator, then you'll always have a current flowing up that line and flowing down that line. And so that will mean that this will continue to flip round. And if we put a little driver on here, that will drive something that will turn. And from that, we've got a motor. Now let's think about the difference between charged particles in an electric field and in a magnetic field. If we take a charged particle, let's take, for example, an electron in an electric field. So here's two plates, one positively charged, one negatively charged. There is an electric field between the two. If you place an electron in that field, it's negatively charged, it will immediately move towards the positively charged plate. By contrast, if you take a magnetic field, here's north, here's south, and there is a field between the north and the south, and you place an electron stationary in that magnetic field, it won't move, it will stay there. But if you have exactly the same arrangement, the north and south poles with the fields, if now you have a moving electron, then that moving electron is the equivalent of a current, and you've got a current flowing in a magnetic field, and that will create a force. Then that exactly the same arrangement, electron stationary. If you take a magnetic field, here's north, here's south, and there is a field between the north and the south, and you place an electron stationary in that magnetic field, it won't move, it will stay there. But if you have exactly the same arrangement, the north and south poles with the fields, if now you have a moving electron, then that moving electron is the equivalent of a current, and you've got a current flowing in a magnetic field, and that will create a force on the electron, and it will bend round in a...
So the field is north to south. The current is right to left. Therefore, the force is away from us. It's going to move into the screen.
A curve. In this case, if we apply the rule of the Fleming left-hand rule, you will find that what the electrons will do is they will curve into the paper. So
Because this is the left-hand rule because it's an electron.
to recap, a charged particle that's stationary in a magnetic field won't move, but if it's already moving, then it will be curved by the force of the magnetic field. Now let's go back to our formula that said that the force was equal to the magnetic field times the current times the length of the wire. Current, we know, is the flow of charge per second, Q over T, where Q is the charge and T is the time in seconds. And the velocity of the charge is the length traveled divided by time, distance divided by time. And that means that T is equal to length divided by velocity, which means that we can now put in this
Velocity? What do you mean velocity of what?
and the velocity of the charge is the length traveled divided by time, distance divided by time. And that means that T is equal to length divided by velocity, which means
Velocity of what? The moving particle?
that we can now put in this formula here, we can say that I equals Q times T. Well, T is L over V. Sorry, I is Q over T. So I is Q divided by T, and T is L over V. So we now have that I is QV over L. But F is VIL. So we can now substitute this for I, and that gives us that F equals V times I, which is QV over L, times L. And of course the L's cancel, and so now that you've got the force is BQV, which is the value of the magnetic field, times the charge on the particle, times its velocity. Now we've just shown that a moving charged particle in a magnetic field will curve. So that now let's have a look at, here's a particle, which is moving but being curved in a magnetic field. And let's say it goes around in a circle of radius r. Well, we can say that the force on that particle is BQV. We just derived that. But we can also say that if anything moves in a circle, then there is a centripetal force acting on it to cause it to do so. And the value of the centripetal force is mv squared over r, when m is the mass of the particle, v is its velocity, and r is the radius of the circle. And those two have to be equal. And that means that BQV is equal to mv squared over r. And if you rearrange that, you'll find that r is equal to m.
Well, he didn't explain that you're going to get a circular motion because it's always if you apply left-hand rule. Let's say the field is into the screen and the motion and the current is up, then the motion is to the left. But it's going to rotate. The same rule will apply as it's turning. Now let's calculate the forces.
mv divided by bq.
Of the radius. Let's see if anyone tried stern-gerlach one at a time. Stern-gerlach one atom at a time. Let's look it up. There's I just need to make sure. Okay, let's look it up. So, stern-gerlach. Why is he upset? This is good. Fraser Kane usually interviews these two guys. It's really interesting. Even though it's very difficult to debate Scott Manley, because he's like a known super duper genius. Okay, stern-gerlach, one sequential. I don't care. What do you mean not about spin? What do you mean not about spin? So what was it about? I can't. Didn't I tell YouTube not to autoplay? Give me a second. Okay, let me just unprivate yesterday's stream. Public. Save. Okay, that's done. Let me go to YouTube. YouTube settings. This channel is temporarily unavailable? I don't believe it.
Let's see. 35, but
I just want to show you. Asmongold's ban. Asmongold is one of the biggest YouTubers.
no. It's located 35, but 35, but I've been 10 minutes late. Still, I'm here. Yeah, you guys should be happy. Jesus. No, I apologize. But yeah, as the goal has been banned, the mainstream media is talking about it, and the thing that amuses me is that the title should be "Streamer banned after apologizing," because everyone is like, "Streamer banned after racist comments." That's not accurate. He didn't have time to apologize, so he made the racist comments against the Islamic race, and after making the racist comments against the Islamic race, he didn't get back. He was actually on Twitch for a couple more hours, and then you had like a lot of streamers that were begging him back. It's like, please, he cannot get away with this. In the United States of America, like, are you insane? Allowing people to think for themselves, that is dangerous. Imagine the chaos that it would do if people have their own takes and opinions. Like, that is haram, okay? And it is blasphemous. Like what he did, he blasphemed against the Islamic race, and as such, he has to suffer the punishment. It's the most American thing to do. So yeah, he got banned, and now I think like even big websites are writing about it. Let's see. Well, actually, no, surprisingly not. I thought that MSNBC was writing about it. But no. It's located to IGN, Comic Books, PC Gamer, The Gamer. A lot of leftist rags, which are very satisfied. Because you gotta understand how it works, right? Usually you have journalists that are ideologues, and they don't really care about video games. What they care about is what you think. And their work is very difficult because you have content creators that make sense. Like you have content creators that are not dealing with the bullshit, and they're just saying things the way they are. And these journalists are seeing it. It's like, if only those content creators wouldn't exist.
So more specifically, welcome back. This is my final video on quantum spin. And in this video, I am finally going to talk about the measurement process. Now, anyone will tell you that the measurement process in quantum mechanics is a very strange thing. But in some sense, it's not quite as strange as many people make it out to be. So I think there are a lot of features of quantum measurement which confuse people because they're not fully explained in usual introductions to the subject. So in this video, I really want to try to get at, what is a quantum measurement and how does it work? And in order to do that, I'm going to begin by looking at this one example of a quantum measurement, namely the Stern-Gerlach experiment.
No, that's not true. I mean, we never had any issue when we measured the mass of an electron, and the charge of an electron. No one had an issue with the quantum measurement. It's only the spin. The problem is just spin. Stop claiming that it's anything else. It's just a spin. That's all.
And by looking at the Stern-Gerlach experiment in a lot of detail, we'll be able to extract some very important lessons about quantum measurement and really get under the hood and see how it works in general. Now, the Stern-Gerlach experiment gives you a way to measure the spin of a particle. So here's the basic setup. So we start with some sort of particle emitter. And the way in which this works isn't, we're not really going to be too concerned about this, but essentially your particle is going to come out of this emitter. It's going to going to the right, and then it's going to enter a zone with a varying magnetic field. So more specifically, let's think about this magnetic field as pointing upwards, so upwards meaning in the z direction. And imagine that the z component of this magnetic field is varying with z, so varying with height. So in other words, the partial derivative of the z component of the magnetic field with respect to the height z is not equal to 0. So the magnetic field is, could be weaker at the bottom and stronger at the top, something like that. And in a bit, we'll talk about how you could create such a magnetic field. But okay, yeah, in this orange region, we have a varying magnetic field somehow, and our particle enters this zone. And then depending on whether the particle is spin up or spin down, it's going to either go upwards or go downwards. So for instance, maybe if it's spin up, it'll go up, and if it's down, it'll go down. And then here we have a back wall of some sort, and the particle will then hit the back wall. So if we just send our particle, through this device, we can look in the back wall to see, okay, was it spin up or spin down? Now, let me briefly refresh you on why a varying magnetic field will make a particle go in a different direction depending on its spin. So in classical mechanics, there is an equation for the force of a magnetic field on a magnetic moment. It's F equals the gradient of mu dot B. So here mu is the magnetic moment of the particle. And depending on the direction of the spin of the particle, this magnetic moment will be pointed in a different direction. So actually, in my last video, I derived this equation in classical mechanics. So if you are curious about where this equation comes from, you can watch my last video. And at the end of my last video, I gave a derivation of where this comes from. But let's just take it as a given for here. Now, you may or may not remember that in classical physics, this magnetic moment vector mu for a charged spinning particle is equal to the charge of the particle q over 2m times the angular momentum vector of the particle. Now, in quantum mechanics, for an electron, for instance, there's this other factor up front called g, where g is the g factor, and it's approximately equal to 2 for reasons having to do with special relativity and stuff, but I talked about that in a previous video too, so let's not get into that. But yeah, so in any case, if the particle intuitively is spin up, then the magnetic moment vector is pointed up. So let's say, that was the case. Then this mu vector would have components of 0, 0, and then its magnitude mu. So this is, just sort of thinking intuitively, if the particle is pointed up. Now, in this case, the force on the particle F is equal to the gradient of, now you see mu dot B is just going to be mu, as in, the magnitude of mu vector, so mu times B sub z. So mu times the z component of the magnetic field. And now we can actually just rewrite this as mu times the gradient of B sub z. And if we're imagining, let's say that this is only varying with height, let's just say that, B sub z only depends on z, then this equals mu times partial B sub z, partial z. Yeah, so we can see that there's going to be a force on this particle if, the magnetic field is changing. And furthermore, if the particle was spin down, if it was pointed in the other direction, then we would have a minus sign here, right? It would be pointed downwards, and there would be a minus sign here, a minus sign here, and a minus sign here. So if the particle is spin up, the force will be in the opposite direction from the particle is spin down. All right, so let me just clear a little bit of this stuff off. Get rid of this too. Now that was a bit of classical intuition, but let's talk about what happens quantum mechanically. So quantum mechanically, the state of our particle is going to be given by a vector of two functions. So we'll have one function called the spin up wave function and another function called the spin down wave function. The spin up wave function, depends on time and the spatial coordinate x. Same thing for the spin down one. And this will tell you the probability density of finding your particle spin up or spin down in a particular location at a particular time. So for instance, the absolute value of the spin up wave function of t and x squared, this is the probability density of finding the particle to be spin up, with respect to the z direction. So when I'm saying spin up and spin down, I implicitly mean with respect to the z direction. To be spin up at location x at time t. And then, for the spin down wave function, the same thing would give you the probability density of finding the particle spin down at location x at time t. Now, I talked about this a lot in my last video, but in many cases, you can think about particles in quantum mechanics as traveling in Gaussian wave packets. So these wave functions will be these little complex wave packets, traveling with some velocity, and the absolute value kind of has like a bell curve shape. And let's say we're drawing the spin up wave function in red, or like maybe let's say we're drawing the real part of the spin up wave function in red, and the real part of the spin down wave function in blue. So we'll be right on top of each other basically. So when the particle is emitted, the spin up and spin down wave functions will be like the same function. But as the wave packet continues to travel to the right and enters the zone of varying magnetic field, then the spin up wave function
and the spin down wave function will evolve in different ways. The spin up wave function will sort of go basically on this upward trajectory, and the spin down wave function will go on this downward trajectory. So that means, for instance, that if you look at, say, this position right here, so like this position in space x right here, the value of the spin up wave function at this particular position will be pretty appreciable. But meanwhile, the value of the spin down wave function at this position will be very small, will be negligible. So, and meanwhile, at this particular position here, and the time in which the wave packet is getting there, the value of the spin up wave function at this position will be negligible. Meanwhile, the absolute value of the spin down wave function here will be appreciable. So in other words, once you've gotten to this point in time when the wave packets are kind of like this, there's a lot of probability that that if the particle is spin up, it's going to be in this region up here, and if the particle is spin down, it's going to be in this region down here, but they'll be spatially separated. Now, while talking about this, there's something I want to point out. Classically, when you have that the magnetic moment vector is proportional to the angular momentum of your spinning particle, your spinning particle in classical mechanics, could be spinning in any direction. Like this L thing could be anything. So, the particle could be spinning up like that, or it could be spinning at an angle, and so on and so forth. And in classical mechanics, you would instead of getting these two different.
I would just make the magnet shorter. If you make it shorter, it's just not going to split. How can we disprove this nonsense? Just send them one at a time. Anyway. Let's refresh this page. Because I turned off the autoplay. Again. I asked for one atom at a time, so no one ever conducted this experiment. They just don't care. You heard the animosity. How dare you offer a solution? You have to go conduct this experiment. It's your obligation to conduct this experiment. It's my obligation. Okay. This troll. He's a troll. I'm a troll. That's it. I'm a troll. That's it. They don't need to debate me. I'm a troll. And they ought to win because I'm a troll. This guy never talks about experiments. It's all about mathematics. Immediately, let's create more and more math. That's the guy we just watched.
Units of h over 4 pi. We've also learned to distinguish between two.
The vitriol, the hatred, the animosity. So I was like, wow. Oh, another person is joining the community and is coming up with fresh new ideas and maybe can resolve a long-standing issue that we've been having and is, basically, another brain power to the rescue. No, it's a troll. Let's make fun of him. And then I tell them, you believe in global warming, but there's so much pressure on any scientist to be part of this consensus. Look at the pressure that you're applying to me about quantum mechanics. This is not political, nothing. Look at the pressure. Look at how much you're trying to hurt my feelings again and again and again. You're all against me. So you think like I'm ready to leave this field. This field is who can stay? The only person who can stay is some conformist who is just in for the money. The only people who end up staying in any community are the worst people. And then the community becomes even more toxic. The most toxic people end up staying in the community. No one has conducted this experiment one atom at a time. I don't think so. It's a beam of silver atoms. It's a beam. Of course they're going to interact with each other. These guys are making this process so painful. It's like, no, we're going to hurt you. It's going to hurt. It's not going to be fun. We're not going to let you have fun. No, you're going to submit to the mob. You're going to submit to the consensus. How dare you question the consensus? Let me just tell. Um, Let me give an invitation to my server. He's typing. Hello. Oh, you're back. Can you hear me?
Yeah.
Hey, can you talk?
Yeah, I will probably sound fairly congested because I'm still, recovering.
Yeah, it's okay.
But, yep.
Thanks.
So, you proposed an experiment. It was a good experiment.
Thanks.
And it's so the answer is it depends on how good your resolution is. So in the stern-gerlach experiment, you launch a particle or a thing that has a magnetic moment through an inhomogeneous field, and it will be deflected according to the force that acts upon it, right?
Sure.
We understand that.
Yeah.
And when you're talking about like a compass magnet or a physical bar magnet, then what you'll get is you'll observe a fairly continuous distribution. That is because there are so many different combinations of the individual particles as being, aligned or anti-aligned, and you have to sum all of those together. So you end up getting a fairly continuous looking distribution. But if you grind it up and you make those little magnets smaller and smaller and smaller, eventually your grains of magnet that you're sending through the thing, eventually they only have 10,000 atoms. And when you have 10,000 atoms, that's going to give you on the order of 10,000 different individual spots, which is going to look mostly like a line. But if you cut it in half a few more times so that you've only got 500 atoms, maybe you start to see them then. But by the time you get down to a chunk of your original magnet that only has like 10 atoms, you can really start to see that it will be discrete lumps. It will not be continuous.
But I don't understand. Why do you say that? Okay, if I throw in like dust size magnets, compasses, you're saying I'm gonna get a continuous distribution? What,
unless you have the resolution to resolve the very, 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 very finely spaced outputs. Yeah.
No, what I'm saying is, why would they look each compass that I'm throwing in, each dust size compass that I'm throwing in, wouldn't it align either up or down?
Yeah, but it will not align. It will not be as strong up or down.
Why? It's either up or down. What do you mean as strong?
Because all of the because it's made out of a whole bunch of individual smaller magnets, which themselves can be up or down.
No, these are wait, I'm taking a bar magnet, so all the atoms are aligned. I thought that's the definition of a magnet. Like a ferromagnet, it could.
Well, they're never always all aligned.
Let's assume we created a ferromagnet, like it's perfectly aligned, and we take a tiny piece, we grind it up into a powder, we throw in one powder piece, and I'm assuming it's going to align either up or down. No?
Okay, so that's actually a version of the experiment that I wasn't contemplating, and yes, if you're careful enough about preparing it before you send it into the machine, because the thing is, you're dealing with like a macroscopic object, and you're probably going to end up. It's really hard to make that thing behave quantum mechanically. You have to have it very, very well isolated.
No, I want it to behave classically. I'm looking. I want to throw in.
Okay. Well, you want it to behave classically, then
it's classical.
Yeah, just throw it in.
Right. It's
what's
classical.
your point?
I think I'm gonna get a right. They're all going to each one I'm throwing in as it goes through. It will align either up or down. No.
No, it won't.
What?
No, because if you because they don't know so this is the part of the experiment where the time that it takes to cross the magnetic field, the particles do not have time to align themselves. They are pushed. They don't align themselves. They either are aligned or they are not aligned. If they had time to align themselves, they would all align and they'd all go to one spot, right?
Wait, what? They would all align like up?
Yeah. If they had to, if when you threw in a silver atom, for example, so here I am going with the original thing. It's either going to be aligned up or down. If you just left it there for an infinite amount of time, eventually it would spontaneously flip to be aligned with the field.
Wait, but it's a very strong magnetic field, and it's a tiny.
Yeah, but where does yes, you're absolutely right. But the energy has to come from somewhere, and the only place the energy can come from is from the exchange of a photon, and that turns out to be a very improbable event.
Wait, I understand.
When you measure.
Wait. I understand that if I take a compass and I put it in the stern-gerlach experiment, it will align.
No, it won't. Not if you're doing a stern-gerlach experiment properly. So a stern-gerlach experiment, you don't leave the thing in there for long enough to flip itself.
Okay, but let's say
that's not how it works.
Wait, but let's say I do. I'm just trying to understand. Let's say I take a compass.
Well, then you're not doing a stern-gerlach experiment.
No, because I'm thinking it's a tiny. Like I'm thinking if I took a tiny magnet under a very strong magnetic field, it will align. I don't know. I honestly.
No, it won't. No, it won't. Is what I am telling you.
Will it recess? Will it do something? Anything?
Yeah, it will. It will process it, but it will. It will project onto one of the allowed angular momentum states, because angular momentum and magnetization are, they occur along the same axis. I mean, the angular momentum is the fundamental, I think, explanation for the magnetization and the charge, of course. It might project as being anti-aligned, and then if it's anti-aligned, it will not just spontaneously flip without.
No. Okay, I honestly don't know. I wish they did like more experiments around stern-gerlach.
Oh, I've done these experiments. If you take a small little magnet, the thing is, the magnets I'm describing are single atoms. And if they are anti-aligned and you just stick them in a gradient, they don't align unless you zap them with a photon. They stay anti-aligned, and they are repelled.
What do you mean zap them?
They don't align themselves.
What do you mean zap them with a photon? Like a light?
I mean, you literally you in this case you use microwaves, but yeah, it electromagnetic radiation.
Okay,
but it has to be electromagnetic radiation of just the right frequency. So I can take a gas of atoms and I can put them into a state where if I apply a magnetic field gradient, they will be attracted to the stronger magnetic field, or I can apply one where they will be repelled from the stronger magnetic field.
But wait. Before
but they don't.
No, I'm confused.
They don't spontaneously.
Wait. I just don't know magnetism enough to understand. Yeah. I mean, I know,
the weird part of this part isn't because of magnetism. This part is because of quantum mechanics.
So I'm trying.
This isn't a classical effect.
I understand.
You're trying to avoid it, but that's not how the world works. Is what I am telling you. The effect that we see in the laboratory can't be explained without quantum mechanics.
Look, the quantum mechanics quote explanation that I've heard is not explanation. It's not an explanation to tell me qubits and cats and dogs alive and stuff.
I wouldn't tell you that. I would tell you some math.
Yeah, I math to me is just words. Like,
and that's fine, but explanations are just words.
Exactly.
Math is just more precise words.
Fine. I need, at the end of the day, the purpose of math and words is to be able to imagine what you're imagining. That's the purpose. I might as well draw.
Yeah, and for a lot of people it works.
For me,
it works. I understand that for you it doesn't work, and that's where you and I run into sort of a wall.
Fine. I mean, but before the wall, that's given. I mean, I have my definition of science that I'm running with. But my question is, I'm just trying to understand. If you take a compass and you put it in the stern-gerlach, it will align. Yes or no? I mean, I don't know.
I mean, if you launch it through fast, like you do in.
No.
Oh, well,
just leave it there. It will.
Yeah. Okay. Yes.
But it will not.
Yes.
But it will slowly lose energy, right? It would precess, and through friction, it would stabilize. Now, it would stabilize always north.
Oh, I mean, I was skipping that part, but I know what you meant. So you were talking about the oscillation. So yeah, it would do that. That's good of you to recognize, because it would do that. As it gets smaller and smaller, eventually you would notice it would deviate from that behavior.
It would stop precessing.
No, it still precess. It would still precess. It wouldn't oscillate. A precession is a rotation in a different axis.
I mean, I could imagine it. I can imagine it just being unstable. Like the forces, whatever. It's basically like a pendulum. At the end of the day, it's going to undulate. Whatever it's going to do, it's not going to stabilize, because whatever forces are applied to it, these forces are not dissipative. So any tiny magnet compass I'm going to put in there, it's not.
There would be some dissipated forces, because there are still moving charges inside the magnet, and those moving charges are still interacting with the field, and are still there's going to be, I think, some dissipation. So certainly, if there's any molecules around.
In a single atom. Wait.
In a single atom, it won't do this oscillation thing. Is what I'm telling you.
Oh.
It doesn't. It precesses, but it doesn't. Like if it was half aligned, if the spin was projected it can't be projected sideways, because once you do this measurement, you project. It's a projection operator. It's very counterintuitive. But the crossover is difficult to describe because it's a very complicated system that then you're suddenly moving into a regime where the math is just fucking awful.
But I don't want to talk about the math. I want to imagine the forces. I want to imagine a free body. Even if I'm imagining a single electron, I'm still mechanical. I'm always in my mind. I want to imagine the mechanics. I want to imagine the physics.
I understand. I understand.
Mm-hmm.
The mechanics that I'm imagining,
Mm-hmm.
and because I am able to imagine this, I understand that may sound really like weird or like a contradiction,
Mm-hmm.
but I am able to imagine this. It's just that I imagine it under a different set of mechanical laws because classical mechanical laws don't apply.
So look, as long as some, I just need mechanical laws. So
well,
as far as I know, we have quantum field theory, we have Feynman diagrams. We have
quantum mechanics is the mechanical laws, the Schrödinger equation.
I know Schrödinger equation to me is just the density, the density of the electron as it's waving around.
Oh, it's more than that. That's why the stern-gerlach experiment is so nice, because the Schrödinger equation totally applies. There are no waves here. It's still called the wave function, but it's better called the state function in this case, because the space of possible outcomes is not continuous like it is when you're talking about the wave function, the position wave function of an electron. The wave function of an electron also has a discrete component. It can either be spin up along an axis, or it can be spin down along that axis.
Look, so in my universe, according to my science, so I need to be able to imagine everything. I can't just accept like up and down. I don't know what that means. I can imagine.
I get it.
So to
I
me,
get it.
like I saw Bohr's diagrams, and I said, yeah, that's basically it. Bohr is basically Schrödinger. I mean, Schrödinger looked at Bohr's diagrams and he copy pasted into a wave equation, and voila, we have Schrödinger's equation. But Schrödinger is just Bohr.
Wow. Okay. That's so not right. But
why not? I mean, Bohr gave us all the I have everything I need from Bohr, right? They took Bohr's theory. Stern and Gerlach took Bohr's theory and they said, this is nonsense. We're going to disprove it. But I understand Bohr's theory. To me, Bohr is completely mechanical, completely classic. And Schrödinger to me, Bohr and Schrödinger are completely classical. I don't have an issue.
That's great. I think we're running into a wall. It was great talking, but I think I'm gonna head back into the other voice chat.
Okay, I'll come in. Let's see if they let me do anything. Okay, I'll see you there.
Because all mistakes would make it smaller and smaller and smaller.
I see. Yep.
And what you don't have there is the graphic of all 7. I did this 7 times. This was just the coup de grace, where I had the 3 simultaneous. And leading up to that, with our other 7, they also return the same freaking radius, except radius on the ellipsoid is instantaneous. So you're dealing with latitude and azimuth and length affect what you're going to call radius of curvature. Because when you're standing on the ground and you drop that plumb bob is not pointing to the center of the earth. It's pointing normal to the geoid, and that will not point at the center of the earth exactly. But in limited areas, you can call it the same. And unless you're doing, a 3,000-mile survey from the Atlantic to the Pacific. And in that case there, I was kind of pleased that we're dealing with 520 miles. I'm very pleased with that. Because you know what the distance from Alexandria to Syene is?
What?
520 miles.
So?
But my measurement there from Maine to Maryland, it's 1/50th of the circumference.
Nice.
So I got 7.5 degrees. So did Eratosthenes.
That's sick.
Yeah, it is. And you want repeatable science. Not only did I repeat in Eratosthenes, I repeated Eratosthenes like just one notch further. I had 3 observers and I was at the same fucking distance.
Nice. Well, they
and
don't
I measured to the same sun.
Gotcha.
And we only employed about $100,000 of equipment and a 3-person crew for like 3 man days.
Wow.
Yeah. Go find that, Flurf. And we didn't do it as a flat earth debunk. We did it for our own edification. This was something, when I brought that forward, it's because I already had it.
Interesting. I got it. Huh.
The tower survey, that was not a flat earth debunk. That's just something I had and had pursued for other reasons. I go, oh, you want measurements? Look, I got a boatload of them. Let's just like open up my my file folder here.
Oh, it's just so funny, they're just grasping at straws to explain it away. I mean, I show them that Eratosthenes measurement and they say, oh, well, you pre-assume the globe. How? Explain.
Well, yeah, then please, these are the raw measurements. What do you make of it?
Well, they're never going to take a look at those.
I know. Nobody has ever come back. Nobody's ever, even with the reciprocal zenith angle, nobody's ever come back with a math issue or a question on that. They just say, oh, you did all the stuff I didn't do. Oh, you didn't take perspective. Oh, you didn't take angular size. Oh, you didn't take Rayleigh. You didn't do this. You didn't do that. I go, you're right. I didn't do any of those things, but I still got the right fucking answer. Does that mean I have to do those things? And these are not Google finds. These are not somebody else's YouTube. These are not cut and paste from a textbook. This was, this is what, some people golf. Okay. I surveyed because I had acquired a bunch of equipment. I'd fallen in the retirement scenario, and I have a very old textbook and very old equipment, and some very new, completely contemporary Jeep.
Wait, we have comments from Blush a while ago, like half an hour ago. I'm just going to yap here since I'm bored. What are you eating? Gum. I'm always chewing gum. If I'm eating, it's gum. He's not a Twitch streamer. Who? I thought he was. Who? Little Mariko. What? I'm just going to yap here. Professor, you'd rather talk to flat earthers than me? I don't get it. Like, at least we're talking science. And over there, they're talking about proving the earth is a globe. Anyway. I don't know what to do.
I didn't mean like that.
and the other times where I see reciprocal, the attempts at reciprocal zenith angles, we're at 1,200 feet. We're 2,000 feet. I go, oh, okay, I'm at 11 miles. right? Let's go big.
I don't see the point. I just don't see the point. Okay. I'm just I don't even know what to do now. I can go back to I don't know, writing papers. I have to do some research how to connect to the OpenAI API. Rogue David Pacman gets destroyed live by Will Kane in brutal takedown. Jesus Christ, what is wrong with this P. Diddy? Korean border. Oh my God. Chinese encircle Taiwan. Is this right? Oh, that's not good. They don't want Trump in. I mean, Trump is not going to play games. He's banned from Twitch. Bibi surprising plan for retaliatory strike on Iran. Okay, let's look at okay, forget about this. Let's look at the API. It's called A1. What's the name of OpenAI's latest AI? OpenAI latest AI version. What's the name? O1. So O1 coding. Let's see what they say.
All right, so the example I'm going to show is writing a code for visualization. So I sometimes teach a class on transformers, which is a technology behind models like ChatGPT. And when you give a sentence to ChatGPT, it has to understand the relationship between the words and so on. So it's a sequence of words, and you have to model that. And transformers utilize what's called a self-attention to model that. So I always thought, okay, if I can visualize the self-attention mechanism and
wait, did somebody text me anything? I love Mr. Slave. This is from a while ago. Who's that? It's strange to me how someone you don't know can be so obsessed with you or make false accusations. Brother is blocked and still yapping into the void. Should I apologize for not being chronically online? Okay. And what's this? Oh, Tapioca Weasel. Okay, we can get rid of this. Okay, we need to get back to this guy.
with some interactive components to it, it would be really great. Just don't have the skills to do that. So let's ask our new model, O1 Preview, to help me out on that. So I just typed in this command and see how the model does. So unlike the previous models like GPT-4o, it will think before outputting an answer. So it started thinking. As it's thinking, let me show you what are some of these requirements. I'm giving a bunch of requirements to think through. So first one is like use an example sentence, the quick brown fox. And second one is like when hovering over a token, visualize edges whose thicknesses are proportional to the attention score. And that means if the two words are more relevant, then have a thicker edges and so on. So one common failure in most of the existing models is that when you give a lot of instructions to follow, it can miss one of them. Just like humans can miss one of them if you give too many of them at once. So because this reasoning model can things very slowly and carefully. It can go through each requirement in depth, and that reduces the chance of missing the instruction. So this output code, let me copy paste this into a terminal. So I'm going to use the editor of 2024. So then HTML. So I'm just going to paste this thing into that and just save it up. And on the browser, I'll just try to open this up, and you can see that when I hover over this thing, it shows arrows, and then quick and brown and so on. And when I hover out of it, it goes away. So that's a correctly rendered version of it. And when I click on it, it shows the attention scores just as I asked for. And maybe there's a little bit of rendering, like it's overlapping, but other than that, it's actually much better than what I could have done. Yeah, so this model did really nicely. I think this can be a really useful tool for me to come up with a bunch of different visualization tools for my new teaching sessions.
No, I don't understand. Mm-hmm. I don't understand why he wanted to abandon the discussion. I don't get it.
Now, if measurements, just like in that 1900s,
They're still talking about all this nonsense, and he's listening? He's not even listening. He's like me. He's deafened. Oh my God. So why don't you come and talk to me? Oh my God. Anyway, whatever. What? Yeah, he feels we hit a wall, that he doesn't want to understand it mechanically. He gave up on understanding it mechanically. He lives in a universe where it's fine not to understand things mechanically, and that's it. He's not gonna. Oh, I can talk to him about his professor's experiment. Let me talk to him personally on the personal line. So, can we discuss the video? The video. Which video? He showed me a video. Is this Bad Science Sunday? Did I miss this? Where's the video? Where he sent me a video. Maybe it was here that he sent me a video. Wait, he sent me links. He didn't send me. Wait, he sent me both. He sent me something. Where is it? It's not in the personal chat. So this is the show that he did. Then he sent me his professor's paper. Where? Oh, probably in the globe trends over here. So let's look for Tappy. From tapioca. Nope. Okay, I'm just gonna ask him. Can we discuss the video that you sent me about your boss's experiment? That's literally it. Oh, you're watching? Wait, are you watching my stream? Have you talked to ChatGPT about your ideas? No, I didn't do that. That might be a good idea. Wait, I didn't. But where are you watching? Can you want to come in and talk? We can discuss it because this is mind-boggling. It's completely incredulous. Have you? Why don't you join me so we can discuss this? Wait, let me take. Before I lose it again, when. Oh, this is the paper, but where's the video? You sent me a video. I don't know where is the video that you sent me that he discussed this paper. Where would it be? It's not in the private conversations. There was no video. I don't remember sending you a video. Yeah, you sent me and I sat and I watched it and I gave you feedback. I commented on the video. Where is that conversation? Maybe it was here? Wait. Was it here somewhere? This is from a while back. No, this is a while back. What? You found it? Maybe this is it.
Lab frame. I can launch
Yes.
this ball.
Yes. This I cannot believe it. I mean, I simply cannot believe it. This is too much. If this is true, this is too much. I would not know how to handle this. I barely understand, but from what I understand, he sent in. Hi. So, look, okay, I mean, this is unbelievable. So, he threw an. Yeah, this is really nuts. So, he threw in a cat, basically, through two slits, and the cat. Basically. Yeah, basically a cat. Yeah. So he threw in a really, really complex system that you're gonna have a hard time saying this is a wave. This is
Yeah.
many, many waves. Many things are waving irrespective to each other. So it's really a complex system. What was it?
Yeah.
Was it a silver atom or was it a molecule? What was it? I don't remember.
This was, I think, I'm pretty sure this was rubidium atoms.
Okay. Okay, that's okay. That's complex enough.
Yeah.
So
it might be strontium, but I think these are rubidium. So yeah.
Okay.
I've worked with both. I've done similar things.
Mhm.
Not at this quite at this scale. I don't work for him. I work for somebody who used to work for him. I work in I work about 500 feet away, probably from their lab, though.
Mm-hmm.
So
you're saying they dropped a big complex atom through two slits? How do they get like
the slits? The slits in this case are they're not slits. They're not like positions. What they're doing is they're hitting it with a laser, and they're putting the atom into a superposition of having absorbed the photon from the laser and not having absorbed it. So part of the wave function of the atom travels upwards, and part of the wave function of that same atom stays at one spot. Then they use more lasers to basically like undo the thing they just did, and those two branches, those two paths that it could take interfere with itself. So single atoms end up interfering with themselves.
Hold on. At the end of the day, basically 50 centimeter.
But it's basic. It's a lot like a double slit experiment, though. Yes.
With 50 centimeters apart, so they dropped a single, and they made sure it's a single atom. They had a single atom.
Well, they do it with many atoms at a time, but the physics is all on the single atom level because these atoms don't really interact with each other much at these densities.
But so
if they're in a Bose-Einstein condensate, then they're all in the same wave function anyway. But that's that's a whole another conversation.
I'm super skeptical of the whole thing. Like I don't have a problem. I view Bohr's model. I love it. It's so mechanical. It's so classic. And
Do you mind if I invite Al Trucker? Al Trucker likes to listen to me talk about this stuff.
Sure, you can invite anyone.
Okay, I'm also going to invite NASA shill.
No, that's useless.
I know, dude. God, I wasn't watching. Was it he who like It doesn't matter.
It's most of them.
It doesn't matter.
It's by far most of them. Most of the time, they're very obnoxious. It's like a religion. It's like a cult. They think that I'm threatening their cult. It's like I'm threatening like their world. I don't know. Like I thought physics is not a cult. They told me science is not a cult. I was told. So I was told, But
I mean, if you're not going to join the cult, then I think I'm done here, and I can go and collect my shell payment. Like, dude, like, yeah, science has a lot of people that agree with each other. From the outside, that can seem cultish.
But they're very violent and vile, and look at how they.
Well,
talk
okay. To be fair, how many of those people are professional scientists?
Fine, but that's all I got. This is
in how many professional scientists do you talk to about this?
You
on Discord, me, and how am I doing so far?
You're the nicest. It's like night and day. You're nice.
So I don't think the problem is with the scientists.
But
is my point.
Yeah, but they're the closest I have. Like I don't have access to you most of the time. I have access to them. Like I need to discuss things with people. I can't think about things forever. Like I had a debate with Sea Lion today, and it was great because he gave me pushback. Like before today, I had a discussion with someone, zero pushback except for he refused to answer questions.
Yeah, you and Sea Lion, I thought that conversation was going somewhere, and it totally would have been going.
No, it was fine. It was fine.
Look, I know, but then it got derailed.
It ran itself dry because he didn't have answers and I don't have answers. So I don't know.
And that was why I showed up, and I tried to give you answers. I understand that they may not have felt comprehensible or valid or a variety of things. I understand that, but I did come and I tried to be like, this is what we would observe in this sort of transition limit between the thing, and it's really weird stuff.
Right.
But
I'm trying
yeah,
to.
but so is this experiment that you wanted to talk about.
Mhm.
It's crazy.
Right, but as soon as you're telling me that like I need to make sure that I know what I'm observing. 'Cause I keep telling you, I'm going to be skeptical. I'm going to ask you, how do you know at every step? How do you know
Yeah.
that you had
Yeah, great.
that you had an atom there? How do you know? And how do you know you didn't have two
So-
or three or many? Like,
Well, you do have many, but that doesn't that just gives you more data. The reason you do this with many atoms is so that because detecting single atoms is very hard.
Sure.
And you have to do it for a long time to get enough data.
Sure.
Whereas if you can do it with 100,000 atoms at a time that are they're spread, but like 100,000 atoms spread over like a cubic millimeter, that's a very dilute thing. Those atoms are really far apart from each other.
They're not
They're not interacting.
Okay. But we don't know.
They're yeah.
We don't know. We don't know. So
Okay. So do we know anything for sure?
I agree. I agree.
The ways here, I can become more quantitative about how we know that they're not interacting. We can describe the
statistics.
We can. Well, yes, but the statistics specifically of how atoms interact with each other, because by a variety of methods, including at these low energies, you can do what's called a multipole expansion, and you can expand the sort of different ways that the wave function can be influenced by a collision into different patterns. And
look,
at very low energies, only one or two of these patterns is relevant, and you can measure that, and I have measured that. I have seen that directly in the data that I have observed. I have watched neutral atoms collide with each other, and I have observed how they scatter into a perfect sphere that is described exactly by this model. It says it tells you if you have atoms that hit each other, there's a probability that they're going to be distributed uniformly all over in any direction. And I can observe that by taking a photo of atoms after they have done that and observing that there is this perfect sphere shell. So that is, and I can then and that is parameterized by a single number called the scattering length. And then you can use the scattering length to describe the interactions of the atoms. It all boils down basically to this one number.
Look, but I need to see a model that I can comprehend. So
then you might need to take some math courses.
No. I want to see a computer. You can show me a computer simulation. Show me a computer simulation of what you think is going on, right? You're not going to be able to do that, right? Right? Because the computer simulation.
Well, I mean, not like immediately.
No.
Like at the drop of a hat. No, I can
no.
totally show you a computer simulation. Though,
no, but the computer simulation is not going to be of atoms. It's going to be of complex mathematical functions that I would just say, I would just roll my eyes. I would tell you I don't care.
That's I get that, and that's where we run into a wall.
But the question is,
you were
no. But
you're rejecting the most useful language that we use to describe these things.
Look, I am curious about the universe. I don't know what it means to be useful. I am curious, and curiosity means it has to make sense. If it doesn't make sense, I'm not interested. I'm not interested in useful. Useful, like
useful. By useful, I mean it makes sense. The math is how it makes sense.
Really?
You can't do physics without math, man. It's like if you tried to explain to somebody how to make change, like when they receive a payment and they have to make change for the payment. If you tried to do that without using math, it's nonsensical.
No, I know math. I know quite a bit of math. I mean, I usually don't brag in these forums. I don't like talking about myself.
Well, then what's the problem with quantum mechanics? It's just some differential equations.
I'm actually like top-notch expert in partial differential equations. That's not my problem.
Well, the Schrodinger equation isn't a partial differential equation. It's an ordinary differential equation, and it's linear.
It doesn't matter. It's just it describes a wave. So Schrodinger said he just said
it describes a state vector is a better way of putting it.
No, not to me. To me, it's a physics. The table in front of me is real. There's actually atoms there. We know we've taken pictures of these atoms. We know there's actually atoms there. So and we see the shells. We see the electron shells when we see atoms. Obviously, that's all we see. I've seen gold. They actually have like a scanning microscope, not an electron scanning, but a physical scanning microscope that they actually, they touch the atoms and then they create a 3D model of what the pin, it touches the atoms themselves, and you can see actually atoms, and you can see the electrons.
Yeah. They're not little balls, though. They're
Yes, they
fuzzy
are.
blobs.
Yeah.
No, they're not solid balls, dude. I know exactly how the technology that you're describing works.
Well,
there's several versions of it.
Mhm.
It uses a little cantilever, and it can be used in contact or non-contact mode, and you're describing it being used in contact mode.
Mhm.
And it goes, and it like physically is pushing on the atom.
Exactly.
But it's not a billiard ball.
It looks like
it's not a billiard ball.
It looks like it. Why not? It looks like.
Because no, it doesn't look like it. It's all fuzzy and stuff.
I mean, I'll show you. Okay, let me look up a picture so that we agree on the picture. A picture of gold. I think it was gold atoms. Should be famous by now. Images.
I mean,
Mm-hmm.
I've seen these things.
Yeah. There it is.
myself.
Oh, really? Amazing. Here's a picture.
Yeah, I went to school for a long time, and this is some of the stuff that I got to see in school. Is my
Wow.
point.
That's incredible. Look. I'm not a denier of any sort whatsoever. I'm just
Really feels like it.
No.
Here's my point.
Yeah.
No. I understand. I think where you're coming from, but there is a reason that you get the reaction you do, because you don't come across as somebody who has an understanding or respect for how much background knowledge you need to understand and exists in the field. It comes across as, it doesn't come across to a lot of people as somebody who is interested and is trying to learn. It comes across as somebody who is claiming that they can overthrow it all.
That is,
and
I don't care to overthrow. I don't care to overthrow. What would I gain from? I don't care about anything. I'm just curious.
Dude, you would gain a lot. Are you kidding me? If you overthrew like all of science, like that'd be awesome.
I would
Like straight up.
Yeah, I would get a lot of chicks. That's for sure. That would be nice. But but
I mean, that might be the one thing you wouldn't get. But
Oh,
yeah,
really? Look.
Yeah, how many scientists are not known for their like game? I mean, Feynman maybe, but
Einstein. I understand that Einstein used to bang just about anything, as far as I know. But he was like a celeb. Anyway, fine. Look, I'm not interested because I see how difficult it is to even converse, and it's so emotional. I have my day job, and I like making money, and I don't care. I'm just curious. I just decided to take some time and figure out quantum mechanics and modern physics because of just because of debates, basically.
But you,
Mhm.
yeah, but you haven't figured them out.
Fine. I didn't. I'm not claiming to. I just.
Okay, well, okay. I interpreted what you just said sort of as claiming to. I
No.
retract that.
No, I don't.
I hear you.
I'm skeptical. You'll always hear me. I'm skeptical. If I have an idea, I would bring it before a forum for cross-examination. And, if they want to cross-examine, fine. If they want to mock me and cross-examine me, then I'm out. I'm not interested in that conversation. But it always turns into me, a cross-examination of me, of why I woke up today and drank coffee. Let's discuss that. They want to waste my time, but my time is too valuable to me. So look, I'm just curious, and I just decided that I'm going to assume the universe is mechanical. Otherwise, I'm not interested. I'm not curious. I'm not curious about a universe that I cannot understand. I'm not like the universe has to make sense to me.
I think you could understand it, but
I gave it a shot. My whole life, I've been listening to all the people like you. I've been listening to you guys since forever.
Well,
I'm unhappy with the results. I'm just unhappy.
Did how many physics courses have you taken? And actually sat down and worked through all of the homework problems?
No, basic stuff.
Yeah. I took 2 physics courses in high school, and that was a long time ago. If that was all I had taken,
No.
I wouldn't know stuff.
No,
Then I went to college, and I spent 4 years in college majoring in physics and mathematics, which you have to know a lot of math to do physics. You just do. It's kind of like how you have to know a lot of English to do literature.
Sure.
English literature, that is.
Sure.
But hold on. I'm not done.
Yeah.
After I spent 4 years as an undergrad, I went to graduate school for 8 years.
Awesome.
Where I took a lot of classes, and I also did a lot of experiments and independent study. I still do independent study. I sit down with a textbook and I go through and I do the problems in the textbook.
Awesome.
Because that is how you learn the details. That's how you really learn and understand something for most people.
Sure,
Maybe
sure.
you're different.
No. Of course. Look. I took time out like 4 months ago, and I've been basically doing nothing but studying physics and math around the clock. And
well, you
and no.
Quantum mechanics shouldn't have come up yet.
No. I have enough background of math and normal physics. That's not my problem. Like normal physics, like I was listening to lectures in cosmology, and that's like simple for me. That's
no.
What?
No, dude. Okay, cosmology is not simple. I'm talking about like Newtonian physics, like
Newtonian is easy for me.
Moments of inertia.
Yeah, in moments of inertia, I can do blindfold. I can teach moment of inertia.
Can you?
Yeah. Yeah, I'm amazing with moment of inertia. Like, sure.
Okay, so if I have an arbitrary, like, mass distribution, how do I calculate the moment of inertia about a given axis?
Well, just you integrate. Well, is it a mass distribution? So you triple integrate over the volume, just the delta xyz times each r as a function of xyz, and you get the moment of inertia about that vector, about that point.
But what are you integrating? What's the integrand?
You're integrating, I guess, the density as a function of xyz. Sure. So triple integrate rho of xyz times r of xyz, or whatever I guess something like that.
You know, for the record,
Mm-hmm.
you should have people challenge you on questions like that more often, because that.
Okay.
I don't know if you got like the power. You didn't.
No, I didn't look it up.
You might have had to add an r squared there term manually.
Oh, really?
From the thing.
Why
Yeah,
not?
because the moment of inertia of a point mass at a radius r from an axis is mr squared, right?
No, no, it's mr. The moment of inertia is just mr. You're thinking maybe mv squared over r or something, like the acceleration, the centripetal force. And moment of inertia is just mg. I mean,
Well, it's not mg. No, it's mr squared.
it is?
It's mr squared, dude. I just looked it up.
Okay. I don't remember. I mean, moment of. Okay, I'm not.
You were okay. You got possibly the most important single detail, like not wrong, but well, yeah, wrong. But
I mean, the question is,
honestly,
I mean, the question is,
you
what?
like the overall idea of that you had to do the integral over the density of this thing. Like that's all correct. So my point was that if you want people to take you seriously, it helps to be able to do something like that.
They don't challenge me on the content ever. It's always how dare I challenge the field? Who am I? You know, they.
Well, then maybe like approach it in a totally different perspective. Maybe you should approach it by asking specific questions that you have answers to that they don't.
Look, I look. I've given. I don't know what to tell you. I honestly. It's not. Look,
I know.
It's not that important. It's not that important.
To be fair, you've only been at it for 4 months. That's just frankly not that long.
Right. Yeah, and you know. Look, no.
People argue with their spouses for way longer than 4 months at a time.
Look, yeah, you're right. The moment of inertia is mr squared. I need to look into that. Anyway,
for the record, I was self-conscious enough that I Googled it and checked before I doubled down.
Yeah, sure.
I was like 98% sure, but 98% sure is just not that sure.
Yeah. Look, it's been a while since I'm trying to even remember what is a moment of inertia. This is like I have to dig into.
This isn't exactly. That's why I chose this particular thing, because the moment of inertia is an intrinsic, like it is the analog of mass in angular momentum problems. Okay.
Sure.
And it is the rotational sort of proxy for just mass.
Right.
Because it also takes into account the lever arm about the axis that you're talking about.
Mm-hmm.
And that is a thing that you can also calculate properties of a wave function by doing the same integral. The difference between a wave function is that when you perform certain types of measurements, you get results that don't seem wave-like.
But look, the point is, I start right. I always start from Planck, Einstein, de Broglie, Bohr, Schrödinger.
You should
Heisenberg. I mean, that,
you should.
Yeah.
You should spend a year grokking Einstein and Hamilton and Lagrange and Jacobi before you try and go on to Bohr and Einstein and Schrödinger and Dirac and Heisenberg and all them. All of the math, all of the physics that comes later requires the tools of the stuff that comes earlier, and developing that.
No, but I look. I look at Planck and his black body radiation and where he got his H, and I can follow the logic. I cannot derive it right now, but well, with the degrees.
Dude,
it's
honestly,
Mhm.
I should be able to derive that right now. That is one of those things that you actually end up deriving over the course of a formal physics education. In like 5 different classes, you derive the black body radiation law. I don't think I actually could, and most people, like most PhD physicists, couldn't. Just like if you just ask them, drop. Like that's why we have notes.
Sure.
Like I have notes that are specifically, these are my definitive I'm deriving the black body law notes so that I can say I don't know necessarily how to do it, but I sat down and I figured it out and I wrote it down and here it is.
Look, the point is I've watched many PhDs and professors online explain it, and I followed. Some of the times I actually followed step by step, and I made sure and I double checked that what they're doing every step is correct, basically. And it makes sense, because still I didn't do it enough, but okay, I'll assume Planck and E equals HF or something. HF, yeah, something like that. Okay,
Yeah,
something like
HF.
that. Whatever that means. I'm not even sure what that means. Okay, we'll come back to that. But fine, let's assume that.
Do you want me to explain it to you?
Sure.
So, F is the frequency.
Right.
In oscillations per second, basically.
Mm-hmm.
And H is Planck's constant.
Right.
And it has units that are annoying because it has units of action, which is joules times seconds, but you could express that in a whole bunch of different ways because joules are equal to kilograms meter squared per second squared, and all of those. You could express that in fucking electrical units if you wanted to, but it doesn't help here.
Mm-hmm.
So it tells you that when you have radiation, electromagnetic radiation of a certain frequency,
Mm-hmm.
that it comes in chunks of that amount of energy. That's all it means.
Right. No. But at this point, I can explain to you the mechanics why that's true. So let me ask you, can you explain to me mechanically, can you derive mechanically E equals HF? Well, what's causing that? Can you explain that? Because I can give you,
No.
So I can bring us down to the size of an atom, a hydrogen atom, and I'll show you exactly why that's true, mechanically, classically.
In terms for a photon? Because there's no mass in a photon.
Fine, that's fine.
There's no particles.
Right, but for me,
okay.
I use the ether model. So for me, everything is a fluid. So
okay.
Yeah, I mean, everything makes sense to me mechanically. So
okay.
So the atom, the hydrogen. Let's talk about the hydrogen atom. So the hydrogen atom, it has a nucleus. We'll ignore the nucleus. It has a proton, a tiny nucleus, and there is an electron waving around. Now, the electron, let's say it's waving at 1 lambda. Now, so it's basically, you can think of it as a wire in terms of electricity. So it's basically an electric current running around in terms of electric current. But physically, it's electric density. These are actually the words of Schrodinger. That's how he described what he had in mind. So it is the density of the electron. There's no probability. The way I view it, there's no probability. It's just
sure.
It's a wave. It's an actual wave. You can think of it like a sound wave. And it's a single lambda when it does 2 pi r, it's a single lambda, and it can't be less than that. That's why it can't collapse. And there's no energy because there's no energy loss.
Okay.
Anyway,
wait.
yeah.
What are we were describing the
E.
Planck relation?
Yes. Now let's imagine a photon coming in, and that's a wave. It's a wave packet. So a wave. So this photon, it smacks against the electron wave, and this smacking, this vibration, it transfers its energy into the system, not into the electron, but into the system itself, into the entire atom. So now,
Yep, you're very right. This is a totally reasonable way of describing what happens. I love it. Go on.
okay, and what you get is this wave now. All the energy has been transferred into this wave, and it has more kinetic energy. And you can think of it also as a rubber band, and it just goes up to the next orbital. And I think it now has more lambdas. There's like
Yeah, no, okay. At this point, the rubber band thing, metaphorically, it kind of works, but
well, it's a rubber band because there is Coulomb's force. So this electron.
Rubber bands get stronger as they pull out. Coulomb's force gets weaker.
Okay, so it's not. I mean, okay, fine. It doesn't matter. So it's not a rubber band. Fine, but okay. So this electron running around, waving around in 1 lambda. Now it went up 1 energy level because that's exactly. It has to be a perfect match. Or maybe let's say it's a perfect match. The amount of energy that the photon had is exactly the amount of energy that the electron needed, quote unquote, in order to go up 1 level. So now it's running around in 2 lambdas. So there's 2 wave crusts running around. And this situation is unstable. It's just, the ball at the top of the hill. It's unstable. And sooner or later, the electron is going to collapse back into its original orbit, and when it falls back, it basically smacks against its minimal possible energy, and that it actually smacks against, you could say, the ether, and it creates a wave, and that's exactly the same photon that it absorbed. And it has some direction, it's but it's when it snaps back. That's why I gave the rubber band analogy. But fine, when it falls back into place, it smacks against its lowest configuration. It can't go any lower, and it falls and it smacks, and that vibration, you can feel it. That is a photon. It's a quantized amount of energy. That's
okay. That does not explain why it cannot occur why you can't have that same frequency of photon at a lower amplitude by a different process.
Yeah, you're right. I didn't think about, all the details. I'm doing this on my own. I never talk about this to anyone.
Okay.
So I wish I could.
Yeah. So that is well, you're doing it now. See?
I wish I could talk to people about this, but everyone I start a conversation with, they start telling me how terrible of a person I am. I'm like, I'm honestly, I don't know what to do with that. Like, there's no one I can talk to. Like, the only person I can finally talk to is like a professor. There's gotta be somebody else.
So okay. I can give you one other person that I'm sure would be willing to talk to you in good faith, and that is Professor Parks.
Oh, I talked to him. Like, you're better. But maybe it's because many people.
He's pretty good though.
Yeah. He's good. But you're better.
So
You're just better. He's a cosmologist. You're like a quantum physicist. Like
You're right. Okay, that's true. Okay, yeah, but dude, if your bar is going to be quantum physicists, then you have one other option in this field, and that's PhD Tony. And yeah, that's not going to work. PhD Tony and you would not get along. I already know this. I feel like Al, you would know better than I would. Al probably can't talk, but I can see what he's saying at the
yeah, I can see what he's saying.
the side chat. So
look, the point is, I can. So the point is, I look at everything completely as much mechanically as I can, and whenever I need to, I do thought experiments. I do a lot of Dunkins on my own. No one is willing to talk me through these. Anyway, so I always start from Planck, and then I add Einstein's what.
How? But the reason that we started this conversation, this is a total derailment, by the way. It's not responding to what you're just saying. Was like this experiment?
Yeah.
With the atoms and the 54 centimeters of separation between different halves of the wave function of an atom.
Yeah.
And you. It's mind-boggling.
Sure, but look, but even the stern-gerlach, I don't have enough information. There's not enough information. I don't have the experiment available to play around with it. I don't have access to anyone. I don't have access to anything. I can just.
Man,
I
wish I had because I've done these experiments. I've done them with falling rubidium atom, potassium atom and rubidium, but longer ago.
But the question is, like, I need to do many variations with tiny magnets and slow and fast and different.
Oh, that's very hard. Yeah.
And different
that experiment genuinely is not actually that's a very hard experiment to do. I'm not bullshitting you. It really is. I don't know how I would do it.
We're talking about stern-gerlach?
Yeah, a good stern-gerlach with powderized like little magnets.
Like that's one version I would love to do. And
I don't know how I would do that. It would be really hard to do that.
Yeah, and
properly.
Like there's so many experiments I want to do. You know what? I was even thinking, like we should be able to, like if we believe in the double slit experiment, we should be able to pour water through a double slit and see a wave pattern coming out of that. Like, imagine you're pouring water through a double slit.
You could probably do that. It would be, I mean, pouring water. No, I don't think that should be possible. I don't think that
in a vacuum.
No,
like water. Water particles.
The thing is, water in a vacuum starts to freeze.
Oh.
It stops being water, and therefore then you've got like little ice particles, and individual atoms of molecules rather of water will 100% absolutely do the whole double slit thing. Like
I don't believe it. I cannot believe it.
We've done it with buckyballs. We've done it with
I know
molecules that are much larger than those.
I know.
I'm sorry you can't believe it.
Look, it's too much. It's too much. No, it's fine.
It's too much what?
No, it's fine. I'm just skeptical. I'm skeptical because what does it mean? You have to interpret.
That's not skepticism.
No. I have to interpret it mechanically. So far I've been able to interpret everything mechanically.
Then use quantum mechanics.
I don't.
Quantum mechanics is mechanics.
No, it's not. No, I use classical mechanics. I'm happy.
Then reality does not have an obligation to live up to your expectations, my guy.
That's fine.
And it doesn't in this case.
That's fine. You can basically. That's between you and me and me. To me, reality is to me what I determine reality is to me.
Okay, yeah.
Reality to me must must make sense. I don't know what it means. I don't know what it means. I literally don't know what it means. What for reality not to make sense to me by definition. So I don't. To me, it's a no go. You're telling me
Reality.
it
I mean,
can't.
by definition, reality is independent of an individual
No,
person's
no, fine,
experience.
fine. No, but right? Reality. I don't know what it means.
Reality.
No, no.
If it doesn't have any like good meaning if it doesn't mean independent of individual's experience. Like you're describing the exact opposite.
No.
Of reality.
Yeah, but listen to the following. So I literally, definitionally don't know what it means for reality not to make sense to me. By definition, I cannot know, right? I cannot know what it means for something not to make sense to me. Let's say
do not know how to respond to that.
No. Let's say, can you understand that 1 + 1 is 3? Can you fathom that 1 + 1 is 3? Can you fathom it? Right? If I compare to 1 + 1 is 2, right? If I tell you, can you fathom
in what context?
In general,
that's an answer that you didn't necessarily want. That okay.
No, compared to 1 + 1 is 2, right? It's easier to think of 1 + 1 is 2. 1 + 1 is 2. You can relate to it. 1 + 1 is 3. You have to do more.
But can you fathom that 2 + 1 is 1?
I can fathom anything. I agree. I'm saying.
Can you fathom? Well, hold on. No, you can't. Clearly, no offense, but
why not?
Yeah. Dude, you've spent like your argument this whole time has been that you can't fathom how the quantum mechanics works. I can. I genuinely have intuition for these processes. That's not. I don't understand the whole theory at every level. I don't. But the parts that you're struggling with, those parts I do. I really do have good intuitions for like.
Okay.
Yeah, I feel like that would behave wonky in this situation. And like, I'd have to like sit down and do the calculation, but there's probably going to be an interference term and you could probably get whichever result you kind of wanted. But I do have the thing that you're saying you demand.
Yeah.
I'm telling you that I have it.
Look, but
but I'm not, but it took a long ass time. And I started when I was a lot younger and my brain was more plastic, which is always helpful.
Sure. But look, everything I study, and I've studied many fields. I've studied, economics and brain science and physics and, cosmology and within physics.
A jack of all trades is a master of none.
Fine, but I've answered questions. If you ask me any question in economics, I have every answer you can imagine. If you want any discussion as deep as you want in finance, we can do it. In brain science, I have a brain.
I do not have the background to be able to test that. I do have the background to be able to test that in physics, and I did so earlier with the moment of inertia question, and I think we both know how that went.
Fine. Look, but the point is, when I'm trying to resolve stern-gerlach right now, and I'm not even trying. What usually happens is like when some problems I cannot resolve, I let them go. I don't care. I'm not going to waste my time trying to answer a question, trying to resolve an experiment. Like I don't have an answer to the double slit, not completely. So I'm going to let it go. There's plenty of physics I can study that makes perfect sense. Like when people say quantum mechanics,
you're not studying it though. You're totally right. There's tons of physics that you can study that totally is completely classical.
Yeah.
Okay.
No, but I'm doing
a lot of cutting edge stuff, but you're not talking about that. You're talking about the quantum stuff where you can't. It doesn't work.
No.
Oh, people way smarter than you and me have tried, and a lot of them who tried to prove each other wrong.
Sure.
And
Yeah, no. My point is, I left quantum mechanics alone for a while. I started doing GR, and I'm doing tensors, and I'm taking many courses in tensors, and I'm still trying to figure out tensors, and
Yo, me too.
yeah. So and I forgot about stern-gerlach, and then Sea Lion gave a lecture yesterday on stern-gerlach, and he invited me, so I went and I watched it, and I started thinking, and I said, I can explain this classically, and here we are, 24 hours later, and I'm not. If I see it's a dead end and I cannot explain stern-gerlach, I'm gonna let it go. It's like most of physics is really simple. 99% of physics is simple. There's no arguments about it. There's a few things we don't understand. Okay, we don't understand stern-gerlach. Fine. We don't understand double slits. Fine. There's a bunch of things we
You
don't.
don't understand it.
Fine. That's what I mean. It's fine.
Okay. Well, you should actually. That also is a thing. Just FYI. Be more clear about that. Will get you places with people because I did not realize that that's what you meant.
Okay.
And it makes you come across totally differently.
Look, I'll try. Look, I don't know how many more times I can explain to people. I'm not a conspiracy theorist.
I get it.
Like, I don't understand. How do people, like, they keep talking to flat earthers? Like, I block flat earthers. I block conspiracy theorists.
I fucking love talking to flat earthers.
No,
okay,
I can't. It's just a waste of time. I want to write my papers. I have so many papers to write.
Do you know who you remind me of?
Who?
Al Trucker. You know who he reminds me of?
No.
You remind me of Daryl.
I don't know Daryl. Look, I'm like like in terms of.
You remind me a lot of Daryl.
Like in terms
Daryl Frost. You should talk to him. You might actually you'll either agree on a lot or you'll hate each other tremendously. But hopefully you'll agree on a lot.
I usually don't hate anyone. Usually people just attack me and then I just let go. Like I block them.
Daryl's mad at me because he thinks I strawmanned him because I did actually unintentionally strawman him on an episode of Bad Science Sunday, which is not the kind of show where I'm like super
That was a good show. That was a good show. I watched it.
Oh, really? You enjoyed it? Yeah, but like, imagine being the subject of it. Like, I'm not nice to the. Look, it's meant to be entertaining. It's not meant to be like a scholarly refutation.
It was good. It was good. Like, I honestly dislike Tucker. Yeah, I dislike Tucker. It was really good. I'm exasperated by Mr. Slave. He's exasperated. And
yeah. I mean, Al Trucker is.
Yeah, some people I rub the wrong way, and it doesn't matter however much I try to, tell them I'm just trying to make sense of the world. It doesn't help. They think they call me a troll, and they call me they call me names. I don't know what to do with that. Look, you saw the way I view the hydrogen atom. To me, the hydrogen atom, like I wish I could spend more time on it and really get and do E equals.
So, do you know what the big problem with the Bohr hydrogen atom is?
No.
The big problem is, do you know what happens when charged particles accelerate, including in a circle at constant velocity, at constant speed, but in a circle?
Yeah, I heard the story that they spiral, they lose energy,
they radiate.
Yeah,
they radiate.
Yeah.
They lose energy. This is a direct consequence of electromagnetism at kind of at any level. Okay, like you can look at it classically, and you can look at it with the full apparatus of the standard model in quantum field theory. And obviously the latter one will get you the more correct answer, but they'll both tell you the same thing, which is that if you just think about a particle going around in a circle,
but it's not a particle.
That sort of simplistic way, that it doesn't work.
It's not a particle. It's waving around. It's not moving. So it's not radiating.
Well, okay, but I thought you didn't like that.
What? What did you say? You didn't like that?
I thought you didn't like that. I thought you didn't like when we're like, oh, they're all wavy and weird.
Are you kidding? What a complete misunderstanding. Of course it's a wave. Of course I like it that it's a wave. It's not a particle. Of course, I believe in the ether model. The ether model does not allow me to introduce particles. Everything becomes a wave in ether, except for the ether particles themselves. The fluid, it's a fluid. These are
Okay,
tiny.
then why are things measured at locations?
These are waves. These are waves with these are.
Yeah, waves aren't measured at discrete singular locations. You can measure a wave and then measure the same goddamn wave, and it doesn't show up at a single point.
Look, I believe
particles do. That's
No.
why they're particles.
No, but like Q of T says, right? Quantum field theory says that an electron is a wave, right? It's waving. It's waving in the electron field. It's something like that, right?
Yes, but the measurement is a discrete phenomenon that projects it onto a particular position within,
I don't know. I like experimentally. Why do you say that? Like in a cloud chamber, right?
Because
because of what you
Go
see,
on.
like because of what you see in a cloud chamber or in a particle accelerator.
Well, because of what I see in a cloud, because what I see in any position resolving detector. If I have a detector that measures that particular operator or observable,
Okay.
then I observe an answer that is one of the eigenvalues of that observable.
So, like when an electron, wait, we're talking about a free electron now. Like when it's free,
We're talking about anything. I mean, at this point, we're talking about completely generic quantum systems. When you measure when you measure a quantum state with respect to some observable, you are going to measure one of the eigenvalues of that observable.
Look, like
eigenstates.
Right, but when I say observe, to me, I can understand a cloud chamber. I've seen electrons in cloud
Yeah.
chambers. I've seen electron positron in a cloud chamber, and I guess you can see them in a particle accelerator. You can basically see them, and the question is, then you can say, oh, they look like particles. Yeah, they look like particles from a distance, but when you get up close, they are waves. They're waves with, the localized waves. That is the nature of the beast. That I can live
Yeah, but
with.
they're always localized. If you have arbitrarily precise position measurement, it will always be localized. That's not a wavy thing, in my opinion.
Why not? To me, yes. I mean, unless
okay. If you think if that's what,
like,
honestly, at this point, I would stop arguing with you, and I would just be like, okay, fine, it's always waves.
Yeah, it's
That's
always
fine.
waves.
I mean, that's more correct than it's always particles.
Yeah,
for sure.
To me, it looks like particles from a distance. So they like a spark looks like particles.
Yeah,
But-
that's how quantum mechanics works.
No, it's from a distance. To me, it's classical. From a distance, anything looks like a particle. An ant, a person looks like a particle from a distance.
That's how.
A planet, a star, a galaxy looks like a particle from a distance.
To be fair, that's still all quantum mechanical.
Fine.
I mean, that's not the most useful way of describing it.
Right, but when you try to observe a phenomenon like a hydrogen atom or a silver atom, then you resort then it only, like when you have the spectral lines of hydrogen, then or the double slit experiment with an electron, then you have to say, okay, it's a wave. It's got to be a wave. There's no way around it. It's a wave. It sometimes behaves like a particle. Well, it does, but it's a wave. It has mass, it has momentum, it has location, it has direction. It has all these things.
Do waves have mass? That's not totally clear.
Well, Fine. It's
like tsunamis have mass. Like that sort of wave certainly has mass. Like when it's like blasted
agree.
onto the shore. But like out on the open ocean, does a ripple, or which is unambiguously a wave, right? A ripple in a pond.
Yeah. I
Does a
agree.
ripple have mass?
I agree. But I can live with it. Like it's borderline. It's enough. It's fine. Like it's right. It's up to me. I'm the decider. I'm curious about the universe.
Well, yeah, I know you're the decider. That's why I'm telling you that you should decide, differently.
No, but I'm happy with the wave model. I'm much.
If you're so happy, why are you going into chats and arguing with people all the time?
Just to have my theories cross-examined, because I thought I have a solution for stern-gerlach. I said, let me present it to have it challenged. Of course, it's not.
Well, okay.
Mhm.
Then you're still looking for something more.
I want to be sure I'm right. I'm. There's so much I can do on my own without interacting with other.
You should.
What?
Yeah, I would like to read your papers.
Fine, I'll send you. Okay. I have basically 2 interesting papers.
Do you remember my
Mhm.
advice from one of our previous conversations, by the way, in terms of communicating your model
math
through? Well, no, that it wasn't just math. Math is a huge part of it. You're absolutely right. I'm not going to shy away from that.
Okay.
But specifically, being extremely step by step.
Even more. Look, I'll show you my paper.
My point is, what you think is very step by step doesn't come across to me as generally.
By the way, I discovered that not only do we not have a quantum gravity theory, we don't have a quantum.
Yeah, no. I mean,
what?
We do, but we have a bunch, and none of them are accepted by experimentalists. So.
Fine. So no, but the point is, Zabine always says. I don't know if you know her, Hossenfelder.
Yeah. No, I know Sabina.
So
she's jaded. Okay. I see her point, but she's really jaded at this point, and I think she's also got a little bit of the YouTube celebrity sort of high.
Yeah.
But on any individual statement, I normally see where 80% of the time at least, I agree with her.
Yeah.
On anything like actually concrete and physics related, generally it's 98% or so. But she talks about a lot of things that aren't necessarily concrete in physics, and I'm just kind of like, yo, it's not that bad. Calm down. Physics is more than this particular corner of the field.
Yeah.
I don't.
Okay,
I'm an experimentalist. We're doing totally different stuff, and our field is alive. Let me tell you, atomic physics is alive.
All right. Look, all I have is people like her that I hear, and she says
That's fair.
We don't have a theory of quantum gravity. Anyway,
Dr. Ben is
Anyway, but we also don't have a theory of quantum special relativity.
Yes, we do.
Can you explain to me the mechanics, the quantum mechanics, the cause and effect
of quantum field theory?
No, the quantum mechanics of special relativity.
That's quantum field theory. Quantum field theory is almost by definition,
relativistic.
And you could use this as a definition. It's the unifying theory of quantum mechanics and special relativity. Quantum field theory is necessarily Lorentz invariant. It's baked into the fundamental model. Is special relativity is baked into the quantum mechanical model. That's what quantum field theory is.
So, can you show me how 2 electrons exchanging a photon is time dilated mechanically? Why it's time dilated?
Certainly not right now.
No,
but
right.
generally speaking, yes.
Mechanically,
I can.
Oh, okay.
Yeah, yes, and in fact, it's actually very elegantly. It at its core is a mathematical thing, which is from classical mechanics. It's the Lagrangian mechanics. You're minimizing the action, so you're minimizing.
But then you're assuming
the sum over all paths. It's a fundamentally like classical mechanical sort of approach to but then you're using them with quantum mechanical objects.
Wait, but you're assuming the least action. I mean, the least action is an assumption.
That's classical though.
But it's an assumption. There's no found. It's not. It's unfounded. It's an assumption. It's an assertion.
Well, I mean, it matches the data.
Fine, but it's not. I wouldn't say that's mechanical. I would
Okay,
say that's
okay. Oh, wow. Okay, then what is mechanical?
mechanical.
Because any
no mechanical is like if you see two billiard balls banging against each other and one knocking the other away. That's mechanical. Like Newtonian.
How does that happen? What the fuck? What? I'm so lost, dude. I no, this doesn't make any sense to me.
Like,
what if those billiard balls are squishy?
No, fine. Right.
How do you describe this? Wait, what? How are you describing? Do you believe in Newton's laws?
I would say Newton's laws are just my experience. So you're saying the least action is the data. That's what you're saying. You're saying the
exactly.
least.
It's the same thing.
Okay. You're saying the least action is your experience. Oh,
it objectively is. I mean,
if
you can, if
that's good.
They're equivalent. You can show.
Yeah.
Though it's mathematical, of course, because that's the language that these models are expressed in.
Yeah.
That Newtonian mechanics is equivalent to Lagrangian mechanics, which is equivalent to Hamiltonian mechanics, which is equivalent to something that I actually don't know much about, Hamilton-Jacobi theory.
Oh, okay.
But I don't know anything about Hamilton-Jacobi.
Well, I'm touching. They're teaching the Jacobian and the Jacobi intensive.
Yeah, same guy. It's the same guy, but I think it refers to a certain possibly permutation of Hamiltonian mechanics.
Okay.
But Hamiltonian mechanics and Lagrangian mechanics are very fundamental models that are used all over quantum field theory.
I gotta figure these things out. That's for sure. Like I took some, like I was watching some YouTube videos on the least action and the Lagrangian. I mean, everything there is really hard. I mean, compare that to Newtonian mechanics, it's like night and day. So I went through a bunch of
yes.
Yeah, it's really.
You're absolutely right.
Yeah, it's crazy stuff. Like the chain, like deriving the.
But it's so elegant. Oh my god, the Euler-Lagrange equation.
Yes,
is so elegant, man. It really is. Like when you sit down and you understand, like the functional stuff. Like, have you sat down and learned Noether's theorem?
No, not yet. I heard about it.
Okay, it's like if you're able to understand the Euler-Lagrange equation, then you're pretty close to being able to understand Noether's theorem.
Okay.
And Noether's theorem is it's the most like beautiful concept in physics, maybe mathematical physics.
I see.
Because it gives you a concrete, quantitative, specific correlation between certain types of symmetry, like the fact that physics is the same now as it was 5 minutes ago,
Yeah.
and conservation of stuff. In that case, mass energy.
Yeah. Yeah,
And
I heard. Yeah,
yeah,
I need to study
it's
symmetries,
it's
like
beautiful.
groups and stuff. Yeah. Yeah, I need to like I don't know what to do. Like every
Yeah.
day but everything I study is so hard. Like tensors, like just tensors are killing me. I don't know what to do with tensors. It's so hard.
Bro, I have been struggling with tensors for 10 years. Okay, I am working my. You know what I'm doing right now?
What?
What I spent today and yesterday doing at work was working through the first chapter of the textbook problems for Sean Carroll's introductory to general relativity textbook called Geometry in Spacetime.
Wow.
And it's the first chapter.
Oh my god.
And I spent all day basically boning up on special relativity.
Wow.
Quantitatively and writing code so that I could be like, okay, I know, like, I wrote this piece of code, so it's me. It's my understanding. But I sat down and I made sure that this was exactly correct for the inputs that I give this function.
Amazing.
So I can give this function a velocity and an angle, and it will give me exactly the Lorentz transformation 4x4 matrix that you use, and all of that. And that's a little like up to section 1.5 of that chapter.
Amazing.
That chapter goes on to a whole bunch of other shit, and it ends with a complete like reintroduction of classical field theory with the Lagrangian and how that applies to quantum mechanics, and like it. And I have a PhD in this. I work at Stanford. Okay, I'm not a dummy. I spent all day working through some introductory tensor stuff that occurs in like section 1.6 and 1.7 of that chapter. Because it's fucking hard. Tensors are abstract geometrical objects that are extremely relevant whenever you want to describe all sorts of geometrical things. Like if you want to describe a building that is sort of leaning to the side and there's a lot of strain between different layers and different floors of the thing and different joints. There's a lot of strain and there's compression and there's tension and there's torque and there's rubbing between surfaces. All of that you can't use. You got to use tensors.
Right. Right. Anyway,
dude, I have to go eat and shit.
Okay.
Not at the same time, but
Okay, I'll let you go. Thank you. I really appreciate your time. You're amazing. You're absolutely amazing.
Yeah.
All right, I'll catch you later. I'll send you my papers, and yeah, I'd love to get some feedback. Sure.
Yep. Talk to you later.
Yeah, I'll talk to you later. Thanks. Bye. Okay, Al Trucker. Oh, Al Trucker. Why can't you talk? Let's see, Al Trucker. He, him, il, Louis, drive. Heavy hauler, motorcycle rider, family man, advocate for patient rights and empathic treatment for healthcare professionals around the globe. Bad Muzak and singing. Oh, you have a channel? And you know physics? You're a trucker that knows advanced physics? How's that possible? So, I'm a busy guy. I've been sick. Physics is my job. Really? Well, you call yourself a trucker and you look like a trucker. How could you be good in physics? That's not possible. Box. Okay. Trucking is because I use it all day. You use physics? How do you use physics? To do what? Wait, are you sick? Lung cam next? You have breathing issues? Let's see. You're welcome. That's yours? Whoa. Jesus. What do you mean physics? That's a trucker. Dr. Tap to see what flows nice. Marmot or weasel. An hour and a half. What are all these?
Good morning, everyone. I still haven't quite figured out what's wrong with me. Tomorrow, they're gonna put a camera in my lungs. I hope everyone has a great day. Good morning, everyone. I still haven't quite figured out what's wrong with me. Tomorrow, they're gonna put a camera in my
Are you
lungs.
better now?
I hope everyone has.
Material science, chemistry, energy, radio transmission, satellite navigation. Okay, we got to talk, but you got to feel better. Hydraulics, pneumatics, friction. Wow. No, I'm still off. Hopefully, a couple more weeks. Wow. I mean, tell me if I can do something. I mean, tell me if I can help. August 18th. Wow. When was your last live? 13 hours ago, you were live.
All right, we're live. Look at that. That's awesome.
So you're fine.
All right, good morning.
But you need to lose weight. Like, how much do you weigh? Like 400 pounds? I'm okay. Just need more rest and physio. Yeah, I'm alive. But I live with obesity. But how tall are you? Are you ginormous? Are you like 6'5", weighing 400 pounds? Because I can see that you're really, really, you really need to lose weight. Why don't you take Ozempic? Did you try Ozempic? You're more than 400 pounds? Are you 500 pounds? Are you like, you take Ozempic? Okay, it's a good start. You're 325? That's not so bad. But are you over 6 feet? Are you 6 feet, 325? Or are you 5'5", 325? How tall are you? Yeah, 5'8", 325. Yeah, you gotta lose some, man. You gotta lose. Like you look. I mean, you don't have any gray hair. I'm assuming you were like in your 40. You're probably early 40s. The eyes, maybe 45, maybe 50. There's no gray hair. 48. I'm built like a like a brick shit house. 48 is okay. You gotta lose weight though. You gotta be thin. Oh, metabolic derangement. Jesus, that's hard. Like, yeah, 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 yeah. Being healthy is really hard. Thin is just weak. No, no. You can be thin. That's like psychology. You got to get over that. You got to You just got to be thin. Just be thin, and that's it. Anyway, I need to go. I need to make some phone calls. We should talk. Let me make you my friend. Where are we? And then you say, yeah. It is when you have it. Yeah. All right, man. I'll catch you later. I gotta go. All right, I'm gonna go. That was like a amazing discussion, like a normal discussion. Like you never have these discussions on Discord. Like the first normal person I meet on Discord, and it's like a professor, a researcher. All right, I'm gonna go. Yeah, I don't know what to say. I don't know what to say. Yeah, I gotta do research on AI. I gotta figure out. I need to use the AI as a trading for trading. I need the AI to give me certain recommendations and stuff. I gotta do that. All right, everyone. I'll catch you later. Bye bye.